There's a story that begins not in the stars, but in the soil. Not with the infinite galaxies of Einstein or the quantum puzzles of today, but with a quiet orchard in the English countryside. The young man sits beneath a tree, and an apple falls. He watches it drop. Simple. Ordinary, but that moment reshapes our understanding of the universe. This is Newtonian mechanics. The framework that defines how the physical world behaves. The language through which we explain nearly everything we see. From falling leaves to orbiting moons. Before Newton, the universe was a riddle. Motions were described, but not explained. Objects moved, but why they moved the way they did was still cloaked in mystery. Sir Isaac Newton gave us more than answers. He gave us a new way of asking questions. His 3 laws of motion, and his law of universal gravitation, formed the backbone of classical physics. They were simple, elegant, and astonishingly powerful. With these laws, we could not only predict the future, but make sense of the past. Imagine trying to chart a planet's orbit using nothing but gut instinct. Imagine designing a bridge without a mathematical model. Before Newton, that's where we stood. Let's begin where the story actually starts. Earth. You throw a ball. It arcs through the air, slows, and falls. It seems obvious now. Of course it falls. Of course it slows down. But Newton forced us to ask, why? Why does it fall instead of hover? Why does it stop instead of glide forever? The ancient Greeks thought the natural state of objects was rest. That motion was unnatural, requiring constant effort. But Newton said no, rest is no more natural than motion. Objects keep doing whatever they're doing, unless something interferes. That's not just a clever thought, it's a principle. His first law says that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. This law, called the law of inertia, is the foundation. It's not about motion, it's about resistance to change. If you're on a train and it suddenly stops, your body keeps moving forward, not because you're clumsy, but because of inertia. Inertia is everywhere. It's why a puck glides on ice longer than on grass. It's why planets keep spinning, and why your coffee spills when the car brakes too fast. But Newton didn't stop with observation. He quantified it. He gave us a second law, one that put numbers to motion. Force equals mass times acceleration. In words, the force acting on an object is equal to its mass multiplied by its acceleration. Push a feather, it moves easily. Push a bowling ball with the same force, it barely budges. The difference is mass. Mass resists acceleration. The heavier the object, the more force it takes to change its speed. And this one equation became the heartbeat of physics and engineering. It's how we design cars, calculate rocket fuel, model roller coasters, and even figure out if your bookshelf will collapse under weight. But what about interaction? Motion isn't isolated. That's where Newton's third law comes in. For every action there is an equal and opposite reaction. If you push against a wall, the wall pushes back with equal force. If a rocket expels gas downward, it moves upward. It's not magic, it's symmetry. Motion is a conversation between forces. When you walk, your foot pushes the ground backward, and the ground pushes your body forward. When a bird flaps its wings, the air resists downward, and the bird lifts up. Everything moves in pairs. Everything pushes and is pushed in return. Now, gravity. The invisible hand that anchors us to Earth. The force we all feel but don't often question. Newton questioned it. He asked, why does the apple fall? Why doesn't it float? And why does the moon stay in orbit, instead of flying off? His answer was universal gravitation. Every object with mass attracts every other object with mass. It doesn't matter if it's a marble or a moon. The force is proportional to their masses, and inversely proportional to the square of the distance between them. That means if you double the mass of either object, the gravitational pull doubles. But if you double the distance between them, the force weakens to 1/4. This law doesn't just explain apples, it explains tides, planetary orbits, and the mechanics of galaxies. It turned gravity from a mystery into a measurable, predictable phenomenon. And with this, Newton did something extraordinary. He unified the heavens and the earth. Before him, people thought celestial bodies followed divine rules, while Earth followed another. But Newton said, no, they follow the same rules. The same gravity that pulls an apple to the ground keeps the moon in orbit. The same motion that launches a cannonball shapes the arc of a comet. This was more than science, it was philosophy. It meant the universe is not chaos but order. but through careful observation and mathematics, we could make sense of everything. Newton's laws became the blueprint for exploration. Engineers used them to build bridges, machines, and engines. Astronomers used them to predict eclipses and planetary alignments. They became the core of physics education, not because they were old, but because they worked. They were reliable, practical, universal. But what's more stunning is how they still work. We live in a world of GPS satellites and smartphones, of fusion reactors and robotic arms, and at the core of these technologies, Newtonian mechanics still hums. Sure, it breaks down near light speed or inside atoms, but for everything from baseball to bullet trains, Newton is still the guide. Not bad for a man sitting under a tree. The laws that move the world didn't just explain motion, they shaped it. They gave us a lens through which to see everything more clearly, and they taught us something even deeper, that the universe is knowable, that with curiosity, logic, and a bit of mathematics, we can reveal the elegant structure beneath the chaos. Inertia, force, reaction, gravity. They're not just ideas, they're the silent rulers of motion. Sometimes, doing nothing at all tells you everything you need to know. Stillness is not silence. Stillness is resistance. It's a force in disguise, not a push, not a pull, but the refusal to be moved. This is inertia, and in Newton's world, it's not just a passive state, it's the defining feature of motion itself. Imagine you're standing on a frozen lake, no wind, no friction, just ice, stretching endlessly in all directions. You give yourself a push, just one, and you glide smooth, silent, unchanging. You don't stop, because there's nothing to stop you. You don't speed up, because there's nothing to push you. You just continue. That's inertia. The world we live in is cluttered with interference, friction, air resistance, gravity, walls, the ground beneath your feet. But beneath all that noise is a deeper law. Objects don't change their motion unless something makes them. They don't start moving without a push. They don't stop without a pull. And they don't turn unless twisted. Newton's first law, the law of inertia, might be the most misunderstood. It's easy to think of motion as effort, as something that needs constant force. Push the cart, it rolls. Stop pushing, it stops. But the truth is that cart doesn't stop because motion fades. It stops because friction fights it. In a perfect world with no friction, no resistance, no gravity pulling it down, the cart would keep rolling forever. That's what Newton saw. That's what others missed. He didn't just look at how things move. He looked at how they try not to. Think of a spacecraft drifting through deep space. No thrusters, no drag, no sound. Just momentum, carved into the fabric of motion. That spacecraft could glide for centuries, untouched, because nothing's there to change its path. That's not futuristic, that's Newton. Inertia is not a thing we feel. It's a thing we experience through its consequences. It's why your body lurches forward when a car brakes suddenly. It's why a dropped phone keeps falling until something stops it. It's why the Earth, spinning through space, doesn't just wind down and stop. And yet, inertia is invisible. You don't see it. You don't touch it. You see what it protects. Motion, or lack of it. You see the persistence of states. Moving things keep moving. Still things stay still, unless something interrupts them. This principle is so deep, so embedded in our universe, that it shapes everything. It defines how stars orbit galaxies. It explains why dust drifts slowly through a sunbeam. It governs the behavior of traffic, of animals, of tectonic plates. And once you notice it, you start seeing it everywhere. You see it in the inertia of daily life. Why it's so hard to start a habit, or break one. Why emotions linger longer than they should. We are, in some strange and poetic way, subject to our own kind of inertia. We keep going until something forces us to change. Now, let's talk about mass. Mass is more than just weight. Weight is how gravity pulls on mass. Mass is deeper. It's how much inertia something has. The heavier the object, the more it resists being moved. Not just by lifting it, but by changing its motion at all. That's why it's harder to shove a truck than a tricycle. That's why a train doesn't stop on a dime. Mass and inertia are twin reflections of the same truth. And motion doesn't care how fast you're going. It only cares if that speed changes. Inertia resists acceleration. It resists deceleration. It resists deceleration. It resists direction change. This is why turning quickly in a car throws your body sideways. Your body isn't confused. It's just obeying inertia. It wants to keep going straight. You're the one changing direction. Motion and stillness, in this view, are the same thing. They're just states. Inertia doesn't favor either one, it just defends them. A satellite in orbit, inertia. A rock resting on a hill, inertia. A skateboarder coasting with no effort, still inertia. And when something does change motion, a push, a pull, a twist, we name that a force. This is the beauty of Newton's first law. It doesn't just describe motion, it creates the requirement for force. It sets the table for the rest of physics. If there were no inertia, forces would be meaningless. Everything would start and stop with no resistance. There would be no need for engines, brakes, muscles, or caution. There would be no predictability, no design, no mechanics. Inertia brings balance. Let's go deeper. When you drop a ball, you're not just watching gravity pull it. You're watching inertia try to keep it still. Gravity wins, yes. But only because it applies enough force to overcome that inertia. If you kick a soccer ball, the speed it gains depends on how much inertia it has, its mass, and how hard you kick. The force. But underneath it all, inertia resists that change. It's always there. And the moment that ball is in motion, inertia protects it. It keeps it moving in that direction until something, the ground, the air, your foot again, says otherwise. We live in a world where change is constant, but inertia is the reason change requires effort. That effort, that force, has a cost, a price. And that's what gives the world its structure, its reliability, its logic. Inertia applies to systems, a spinning planet, a swinging pendulum, a drifting storm. They all want to keep doing what they're doing, and it takes energy to make them stop, or shift, or reverse. This is why stopping a spinning top is harder than starting it. It's why the Earth doesn't suddenly spin in the other direction. It's why weather patterns carry momentum. And it's why energy is precious, because it's what lets us overcome inertia. Inertia is not just a rule, it's a lens. Through it, we see motion for what it really is. Not a force, but a preserved state. Not something added, but something defended. When you're riding a bike and coast with no hands, that's inertia. When you toss a frisbee and it glides smoothly, that's inertia. When you sleep on a train and don't feel the motion until the brakes hit, that's inertia. It's so subtle you forget it's even there. But it never forgets you. It governs every step you take, every object you touch, every motion you initiate or resist. And when Newton wrote his first law, he wasn't just describing a fact of nature, he was describing a condition of the universe, one that speaks quietly but firmly. Nothing changes unless something makes it. In a chaotic world, that's a strange kind of peace. Acceleration is not the same as speed. Speed is how fast you're going. Acceleration is how fast you're changing that speed. It's not how fast you move, it's how fast you shift. And at the heart of every shift, every change in motion is Newton's second law, force equals mass times acceleration. In words, the force on an object equals its mass multiplied by how quickly it accelerates. This law is not poetry, it is precision. It is the backbone of every calculation that engineers and scientists rely on, and it tells us one fundamental truth. If something is heavy, it's harder to move, and the faster you want to change its motion, the more force you need. It's simple, but it's everywhere. You're standing at the base of a hill, there's a shopping cart in front of you. It's empty. You give it a push. It rolls up easily. Now it's full of groceries. You push again, but this time, it resists. You're applying the same force, but the mass has changed, so the acceleration is smaller. This is the second law in action, and this law doesn't care what you're pushing. A rocket, a wheelbarrow, a human body. The relationship is always the same. Force equals mass times acceleration. If you want more acceleration, you need more force, or less mass. If you increase the mass and keep the force the same, the acceleration drops. This equation isn't just a rule, it's a language. It translates movement into math. It lets us design machines that move the way we want. Cars, elevators, airplanes. They all depend on it. Every acceleration you've ever felt, every push you've given or taken, has followed this principle. Let's slow it down even more. Imagine a soccer ball and a bowling ball, side by side. You kick both with equal strength. Which one goes farther? The soccer ball. Why? Same force, smaller mass. So it accelerates more. Now reverse it. Suppose you want both balls to reach the same speed. You'll need to kick the bowling ball harder, more force, to overcome its greater mass. This is Newton's second law playing out in your muscles, your joints, your breath. It's not theory, it's your life. The law also works in reverse. If you know the mass of something, and you measure its acceleration, you can calculate the force acting on it. This is how we diagnose motion. We look at what's changing, and we ask, what caused it? What force is behind it? Every time a plane takes off, its engines deliver force to accelerate its massive frame. Every time you slam the brakes in a car, the wheels apply a backward force to reduce your speed. Every time a sprinter explodes off the blocks, force propels them forward, balanced precisely against their mass. This is the power of Newton's second law. It links cause and effect. Force causes acceleration, and the amount of that acceleration is shaped by mass. Now let's look at direction. Acceleration is not just a number, it has a direction. So does force. Push an object north, it moves north. Push it east, it turns. This means motion is more than just movement. It's guided change. It's targeted influence. And every change in direction is a kind of acceleration. When a car turns, the wheels apply force sideways, not to speed it up or slow it down, but to change where it's going. That too is acceleration. You see this in circular motion. A satellite in orbit constantly changes direction. Its speed might stay constant, but its velocity does not, because velocity includes direction. So even if it's not speeding up, it's accelerating, and gravity provides the force. The same rule applies to a child swinging on a playground, a marble in a bowl, or the moon circling Earth. Constant redirection requires constant force, and the bigger the mass, the more force it takes. This is not theory, this is nature's accounting. Think of a crane lifting a steel beam. The beam has mass. To accelerate it upward, the crane must apply force greater than gravity, and once it's moving, to stop it, to decelerate, force must be applied in the opposite direction. Every stage of motion from stillness to speed to stop is governed by the same formula. Force equals mass times acceleration. We use this law to calculate fuel for rockets, to plan braking systems for high-speed trains, to design seat belts that reduce injury by managing deceleration. It's even behind sports. How fast a tennis ball leaves a racket. How hard a boxer must punch to knock back an opponent. Every moment of dynamic motion is a silent agreement between force, mass, and acceleration. But what happens when force isn't enough? What happens when an object doesn't accelerate, even when pushed? Then we know there's another force, balancing it. This brings us to net force, the total force acting on an object after all the forces are added up. If the net force is zero, the object doesn't accelerate. It might still move, but its motion won't change. This is why you can push a table and see no result. Friction might be cancelling out your force. It's why standing on the floor doesn't make you fall. The upward support from the floor balances your weight. No net force, no change. Only when there's imbalance does motion change. Force equals mass times acceleration. This one sentence explains why speeding up is hard, why stopping fast is jarring, why turning quickly pulls at your body. It explains collisions, takeoffs, landings, and throws. It describes motion in a way that's testable, calculable, dependable. It's not just a formula, it's the law that lets physics predict the future. Push your hand against a wall. Feel the pressure in your palm, the tension in your arm. You're applying force, but that force is not vanishing. It's coming back at you. This is Newton's third law. For every action, there is an equal and opposite reaction, and it may be the most poetic law in physics. It tells us that force is never alone. Every push creates a pushback. Every pull invites a counterpull. Motion is not a one-sided act. It's a conversation between objects. The more you push, the more resistance you receive. This isn't optional. It's nature's rulebook. When a rocket launches, it hurls exhaust gases down into the Earth's atmosphere, and those gases push back. The result? The rocket moves upward, not because of the flames or noise, but because of the symmetry of force. The gas goes one way, the rocket goes the other. Two actions linked, one motion mirrored. When you swim, your hands push the water backward. but the water pushes your body forward. You move not by dragging yourself through water, but by engaging in a force exchange. The more force you apply behind you, the faster the water pushes you ahead. Birds fly because their wings push air downward. The air, in turn, lifts them upward. Walk across the floor, and your foot pushes the ground back. The ground responds by pushing you forward. You think you're stepping, but really, you're being pushed forward by Earth. It's easy to miss this because the Earth is massive. It doesn't visibly move when you walk across it, but it does respond. Every step you take sends an equal and opposite impulse through the planet. It's just that your mass is tiny compared to Earth. So your motion is obvious, and the Earth's is imperceptible. This law works in all directions. Bounce a ball off a wall, the wall pushes back. Fire a gun, the bullet goes forward, and the gun recoils backward. Jump off a small boat, and the boat slides the other way. These aren't coincidences, they are inevitabilities. Now think of how you sit in a chair. You're not falling, even though gravity is pulling you down. Why? Because the chair is pushing up with equal force. That balance is invisible, but without it, you'd be on the floor. Even when you lie on a bed, or lean against a door, or lean into someone else's hug, you are experiencing Newton's third law. It's not just movement, it's presence. It's the reason structure exists. Newton's third law is not just a law of mechanics. It's a law of relationships. It says that no force exists in isolation. Every interaction creates a response. Every push echoes. You might not always see the reaction, but it's there. When wind brushes against a mountain, the mountain pushes back. When the moon pulls on Earth, creating tides, Earth also pulls on the moon, shaping its orbit. The moon is gradually moving farther away because of this mutual exchange of forces, a celestial dance of give and take. This reciprocity shapes the universe. Galaxies interacting through gravitational forces, atoms bound by equal and opposing electromagnetic attractions, collisions, explosions, springs and balances, all of them are guided by the third law. Even earthquakes are governed by this. When tectonic plates grind against each other, the stress builds up. One slips. The ground lurches. Force released. Equal force returned. A violent negotiation beneath the crust. Even walking relies on this. If the ground were ice, you couldn't push it backward, so it couldn't push you forward. Without friction, the force you apply has nothing to push against. No action, no reaction, so motion vanishes. Try walking in space, where there's nothing to push against. You can flail your arms or kick your feet, but you go nowhere, because the third law demands a partner, and space gives you none. The third law is not about energy. It doesn't say anything about speed or direction. It simply insists on balance. Force from A to B means force from B to A. Same strength, opposite direction. Always. This is why a rocket in space still works. Not because there's air to push against, but because gases expelled backward push the craft forward with equal force. It's a self-contained interaction. The fuel becomes the partner. No atmosphere needed, just mass, expelled forcefully, and the reaction that drives exploration. Consider a trampoline. You jump, and it pushes back. The harder you land, the higher it sends you. It stores the force and returns it. Or a hammer striking a nail. The hammer pushes the nail down. The nail pushes back. You feel the sting in your hand. Your bones absorb the reaction. And yet the hammer still drives the nail, because your muscles apply more force than the nail's resistance. That's the key. Equal and opposite doesn't mean no motion. It just means mutual influence. Whether or not anything moves depends on how all the forces add up. If other forces balance out the reactions, you might see no result. But the pushback is still there. Push against the side of a building. It doesn't fall. You don't fly backward, because your force isn't enough to overcome structural resistance. But it's still returned. Let's go microscopic. At the level of atoms, the third law still rules. When two atoms bond, each pulls on the other. Their electrons and nuclei push and pull in perfect symmetry. It's this balancing act that makes chemistry possible, that gives molecules structure, that allows life itself to build stable shapes. Without equal and opposite forces, matter would fall apart. Every bond in your body, from water molecules to DNA spirals, is stabilized by this law. You are, in every sense, constructed from balance. In technology, we harness the third law constantly. Jet engines, fire extinguishers, railguns, propellers, all of them push mass one way to move in the opposite. It's not propulsion. It's trade. Give motion, get motion back. Even the seat you're in is reacting. Your weight pushes down, the seat pushes up, and you remain suspended because those forces are balanced. You are stationary because the world pushes back at just the right strength. We use this principle to stabilize skyscrapers, dampen shock waves, and create balance in robotics. Counterweights, gyroscopes, landing gears. They all rely on actions being mirrored by equal reactions. The third law makes engineering predictable. It makes construction safe. It lets us ride, land, dock, and launch with confidence that every force will be returned. This is why balance is never guessed. It is measured. It is calculated. This law gives us elegance. It gives us conservation. It reminds us that no action in the universe ever goes unopposed. Not out of punishment, but out of principle. Nature holds itself accountable. Motion demands balance. Force invites return. Energy can be spent. But force always comes with a reply. You can try to push the world, but the world will push back. Equal, opposite, every time. That's not resistance. That's reality. That's structure. That's truth. This is Newton's third law, the law of echoes. The law that says you are never alone in action, because the universe will always respond. Falling is not just a matter of gravity, it's a matter of freedom. The freedom from resistance. Imagine stepping off a cliff. For a few short seconds there's nothing but air. No ropes, no ground, just the pull of the earth. This is free fall. But it's more than a dramatic drop. It's the purest form of Newton's ideas. Free fall is motion under gravity's rule alone, no friction, no engines, no interference. Just one force. In a vacuum, a feather and a hammer fall at the same rate. It's not a trick, it's Newton. Mass doesn't matter in free fall. Acceleration due to gravity is the same for all objects. Galileo hinted at this from the Leaning Tower of Pisa. Newton proved it mathematically, and astronauts on the moon demonstrated it before the eyes of the world. On Earth, the acceleration due to gravity is about 9.8 meters per second squared. That means for every second an object falls, its speed increases by 9.8 meters per second. After 1 second it's falling at 9.8. After 2 seconds, it's almost 20, and so on. This steady increase is what gives freefall its terrifying beauty. It starts slow, then it rushes. Now picture skydivers. At first, they accelerate, pulled by Earth. But then the air begins to push back. The faster they go, the more resistance builds, until at last, they reach terminal velocity. That's the speed where gravity's pull and air resistance become equal. The skydiver stops accelerating. They keep falling, but at a constant speed. It feels like floating, but it's a balance. One force pulling down, one force pushing up. If you changed the shape of your body mid-fall, spread out or tucked in, you'd change your resistance, and you'd change your speed. This is not magic. This is fluid dynamics, meeting Newtonian force. In space, however, there is no air, no drag. Objects in freefall are in perpetual acceleration, limited only by other gravitational forces or collisions. Think of satellites. They are in freefall, not floating, but falling. Falling so perfectly sideways that they miss the Earth again and again. Their trajectory is not stillness, it's precision. They are dancers on an invisible curve. The International Space Station orbits like this. So do planets, moons, comets. Freefall is not just a downward drop. It's a path carved by gravity through space. And it's not exclusive to Earth. Every celestial body has its own gravitational pull, its own freefall acceleration. The Moon's is about 1/6 of Earth's. Mars pulls weaker. Jupiter pulls stronger. This variation affects everything, from how we design landers to how we walk in space. Imagine dropping a wrench on Mars. It would fall slowly, gracefully. On Jupiter, it would slam downward with crushing speed. Gravity's strength sculpts the dance of falling. When astronauts train for zero gravity, they ride in airplanes that dive in parabolic arcs. For brief moments, the plane is in free fall, and so are the people inside. They float, Not because there is no gravity, but because the entire plane is falling with them. Relative to the aircraft, they feel weightless. That illusion is what we call microgravity. It's not fake, it's physics. Freefall creates the sensation of weightlessness, even when gravity is present. It's just that nothing is resisting your fall. This is how orbiting astronauts live. They are always falling. But they never land. They fall forward at the same rate Earth curves away beneath them. And this idea, the constant fall, ties back to Newton's mounting cannon thought experiment. Fire the cannon fast enough, and the ball falls forever around Earth. That's orbital velocity. To escape Earth entirely, you need even more speed. That's escape velocity. On Earth, it's about 11.2 kilometers per second. Reach that, and gravity can't bring you back. You're still being pulled, but not enough to stop you. You are beyond return. This is how we send probes to Mars, to Saturn, to the edge of the solar system. We overcome gravity with speed. We fall so fast and far that we never fall back. But if we stop pushing, gravity always wins. It is patient. It waits. Freefall also tells us something about measurement. Drop an accelerometer, and it reads 0 in freefall. Why? Because it no longer feels a force against it. Gravity acts on every part equally. No tension, no compression, just motion. And from the perspective of the object, there's nothing pushing on it. That's what Einstein meant when he said that a person in freefall feels no gravity. It's there, but they can't feel it. Einstein took this further and said, maybe gravity isn't really a force at all. Maybe it's the bending of space-time. But Newton gave us the language first, and his ideas still guide every drop, every orbit, every leap from the edge of space. The human body knows this too. In microgravity, fluids shift. Balance is disrupted. Bones lose density. Muscles weaken. We are built for Earth's pull. And without it, we change. This is why space exploration is not just a technical challenge. It's biological, psychological, philosophical. What does it mean to live without the constant tug of gravity? To fall forever? To float without resistance? Free fall is the most honest motion. It's motion unresisted, motion unopposed. It's what the universe does when nothing gets in the way. It's how planets move. It's how stars collapse. It's how black holes consume. From the falling apple to orbiting satellites. From high dives to moon landings. From the edge of a cliff to the edge of the cosmos. Free fall is Newton's fingerprint on motion. Simple, relentless, profound. Stillness is not silence. Stillness is resistance. It's a force in disguise, not a push, not a pull, but the refusal to be moved. This is inertia, and in Newton's world, it's not just a passive state, it's the defining feature of motion itself. Imagine you're standing on a frozen lake, no wind, no friction, just ice, stretching endlessly in all directions. You give yourself a push, just one, and you glide smooth, silent, unchanging. You don't stop, because there's nothing to stop you. You don't speed up, because there's nothing to push you. You just continue. That's inertia. The world we live in is cluttered with interference, friction, air resistance, gravity, walls, the ground beneath your feet. But beneath all that noise is a deeper law. Objects don't change their motion unless something makes them. They don't start moving without a push. They don't stop without a pull. And they don't turn unless twisted. Newton's first law, the law of inertia, might be the most misunderstood. It's easy to think of motion as effort, as something that needs constant force. Push the cart, it rolls. Stop pushing, it stops. But the truth is that cart doesn't stop because motion fades. It stops because friction fights it. In a perfect world with no friction, no resistance, no gravity pulling it down, the cart would keep rolling forever. That's what Newton saw. That's what others missed. He didn't just look at how things move. He looked at how they try not to. Think of a spacecraft drifting through deep space. No thrusters, no drag, no sound. Just momentum carved into the fabric of motion. That spacecraft could glide for centuries, untouched, because nothing's there to change its path. That's not futuristic. That's Newton. Inertia is not a thing we feel. It's a thing we experience through its consequences. It's why your body lurches forward when a car brakes suddenly. It's why a dropped phone keeps falling until something stops it. It's why the Earth, spinning through space, doesn't just wind down and stop. And yet, inertia is invisible. You don't see it. You don't touch it. You see what it protects. Motion, or lack of it. You see the persistence of states. Moving things keep moving. Still things stay still, unless something interrupts them. This principle is so deep, so embedded in our universe, that it shapes everything. It defines how stars orbit galaxies. It explains why dust drifts slowly through a sunbeam. It governs the behavior of traffic, of animals, of tectonic plates. And once you notice it, you start seeing it everywhere. You see it in the inertia of daily life. Why it's so hard to start a habit, or break one. Why emotions linger longer than they should. We are, in some strange and poetic way, subject to our own kind of inertia. We keep going until something forces us to change. Now, let's talk about mass. Mass is more than just weight. Weight is how gravity pulls on mass. Mass is deeper. It's how much inertia something has. The heavier the object, the more it resists being moved. Not just by lifting it, but by changing its motion at all. That's why it's harder to shove a truck than a tricycle. That's why a train doesn't stop on a dime. Mass and inertia are twin reflections of the same truth. And motion doesn't care how fast you're going. It only cares if that speed changes. Inertia resists acceleration. It resists deceleration. It resists deceleration. It resists direction change. This is why turning quickly in a car throws your body sideways. Your body isn't confused. It's just obeying inertia. It wants to keep going straight. You're the one changing direction. Motion and stillness, in this view, are the same thing. They're just states. Inertia doesn't favor either one, it just defends them. A satellite in orbit, inertia. A rock resting on a hill, inertia. A skateboarder coasting with no effort, still inertia. And when something does change motion, a push, a pull, a twist, we name that a force. This is the beauty of Newton's first law. It doesn't just describe motion, it creates the requirement for force. It sets the table for the rest of physics. If there were no inertia, forces would be meaningless. Everything would start and stop with no resistance. There would be no need for engines, brakes, muscles, or caution. There would be no predictability, no design, no mechanics. Inertia brings balance. Let's go deeper. When you drop a ball, you're not just watching gravity pull it. You're watching inertia try to keep it still. Gravity wins, yes. But only because it applies enough force to overcome that inertia. If you kick a soccer ball, the speed it gains depends on how much inertia it has, its mass, and how hard you kick. The force. But underneath it all, inertia resists that change. It's always there. And the moment that ball is in motion, inertia protects it. It keeps it moving in that direction until something, the ground, the air, your foot again, says otherwise. We live in a world where change is constant, but inertia is the reason change requires effort. That effort, that force, has a cost, a price. And that's what gives the world its structure, its reliability, its logic. Inertia applies to systems, a spinning planet, a swinging pendulum, a drifting storm. They all want to keep doing what they're doing, and it takes energy to make them stop, or shift, or reverse. This is why stopping a spinning top is harder than starting it. It's why the Earth doesn't suddenly spin in the other direction. It's why weather patterns carry momentum. And it's why energy is precious, because it's what lets us overcome inertia. Inertia is not just a rule, it's a lens. Through it, we see motion for what it really is. Not a force, but a preserved state. Not something added, but something defended. When you're riding a bike and coast with no hands, that's inertia. When you toss a frisbee and it glides smoothly, that's inertia. When you sleep on a train and don't feel the motion until the brakes hit, that's inertia. It's so subtle you forget it's even there. But it never forgets you. It governs every step you take, every object you touch, every motion you initiate or resist. And when Newton wrote his first law, he wasn't just describing a fact of nature, he was describing a condition of the universe, one that speaks quietly but firmly. Nothing changes unless something makes it. In a chaotic world, that's a strange kind of peace. Friction is not a flaw in motion, it's the reason motion ever ends. Every stop, every slowdown, every turn of a wheel that doesn't keep spinning forever, that's friction. And it's not the enemy, it's the unsung counterforce. The quiet guardian of stability. Without it, we would slide endlessly. No grip, no control, no pause. When you push a book across a table, it doesn't glide forever. It slows. It stops. Why? Because microscopic bumps and ridges in the surfaces catch on one another. They resist the slide. Friction isn't just a break. It's a contact handshake. One object saying to another, I'm here. I feel you. I'm holding back. There are two main types of friction, static and kinetic. Static friction prevents motion from starting. Kinetic friction resists motion that's already happening. Try to push a heavy couch. At first it doesn't move. You push harder, still nothing. Eventually it budges, and once it's moving, it becomes a bit easier to keep going. That's static friction giving way to kinetic friction. Static friction is often stronger because breaking stillness takes more than maintaining motion. It's the hill at the beginning, the nudge needed to break the bond between surface and object, and once motion begins, kinetic friction takes over, still resisting but less intensely. Friction depends on two key factors: the nature of the surfaces in contact, and the normal force, the perpendicular force pressing the surfaces together. Not the surface area, that's a common myth. More contact doesn't mean more friction, unless the pressure per square inch changes. Instead, it's the roughness, the material, and the weight. Slide a block of wood on sandpaper, then on glass. One grips, the other glides. Same weight, same shape, different friction. Now consider air. It's a fluid, and it creates resistance too. We call it drag. It's a cousin to friction, only it acts on objects moving through air or water. The faster you move, the more drag you encounter. Skydivers, cyclists, race cars, they all cut through air like a swimmer through water. And the shape of their motion determines how much resistance they feel. This is why engineers obsess over aerodynamics. Smoother shapes mean less drag. Less drag means more speed. Imagine throwing a ball. In a vacuum, it would keep going forever. But in air, it slows. The molecules push back, like invisible hands. Friction is not just about contact. It's about response. The universe pushing back, saying, "Are you sure?" Friction does work. In the physics sense, it transfers energy. But it doesn't give motion. It takes it. It converts kinetic energy into heat. Rub your hands together. Friction warms them. That's energy leaving motion and becoming thermal. Every car brake, every tire screech, every meteor streaking across the sky, they glow because friction burns. It's also why machines need lubrication. Oil, grease, these reduce friction. Make parts slide instead of scrape. Because while friction brings control, too much of it brings wear, tears, grinding, heat that breaks instead of balances. So engineers play a delicate game. Enough friction to hold, not enough to halt. Nature plays the same game. Geckos can walk up walls because of microscopic hairs on their feet that generate friction through van der Waals forces. They don't slip because they're literally holding on at the atomic level. Snow tires, hiking boots, rock climbing chalk, they all enhance friction to grip the unpredictable. Meanwhile, skis and ice skates minimize it to let you fly across frozen surfaces. Friction isn't good or bad. It's a choice, a tool. When you walk, you push backward. Friction between your shoes and the ground pushes you forward. No friction, no walk. You'd flail, fall, drift in place. Friction gives us traction. Friction lets us stand. In space, where there's no air and no ground, friction fades, and motion becomes pure, but it also becomes uncontrollable. A satellite that spins, it won't stop, unless another force intervenes. That's why space stations have gyroscopes and thrusters, artificial ways to do what friction does on Earth. Even earthquakes are born of friction. Tectonic plates push against each other, locked by enormous static friction, until, suddenly, it breaks. The ground shifts, energy releases, and the Earth trembles. Friction holds the world still, until it doesn't. And when you sharpen a blade, strike a match, ride a bike, or open a door, friction is with you, not visible, but vital, not loud, but powerful. It reminds us that every motion is answered, that every surface speaks. Friction is the art of motion meeting resistance, not to end it, but to shape it. In every stop, every grip, every glide, Friction is Newton's whisper. Motion isn't free. There is always something to overcome, and sometimes that something is the reason we can move at all. Curves are deceiving. A ball on a string, a planet around a star, a child spinning on a carousel. These are all examples of motion that look stable, even gentle. But underneath that calm exterior is constant change. Circular motion is not a straight line story, it's a dance. Always turning, always bending. And what keeps it going is force. Specifically, centripetal force. In circular motion, an object is constantly accelerating. Not because it's speeding up, but because it's changing direction. Acceleration isn't just about getting faster, it's about changing velocity. And since velocity includes direction, moving in a circle means constant acceleration. This might seem strange. You drive your car in a perfect circle at a steady speed. You feel fine until you take your hands off the wheel, then the car drifts outward. Because without a force pulling you inward, your body wants to go straight. That force pulling you in, that's centripetal force. Centripetal means center-seeking. It's not a type of force on its own. It's a role played by other forces. When you whirl a ball on a string, the tension in the string is the centripetal force. When a car turns a corner, it's the friction between tires and road. When Earth orbits the Sun, it's gravity. When an electron orbits a nucleus, it's electromagnetic attraction. Different sources, same role, keeping something on a curved path. Without centripetal force, things don't just spiral out, they fly off tangentially, straight, because that's what inertia demands. In the absence of a net inward force, the object leaves the curve. It continues in a straight line in the direction it was going, the moment the force vanished. That's why slingshots work. You spin the rock around, then release. And the rock doesn't continue in a circle, it shoots off in a straight line. It was never going in a circle, it was constantly being forced to turn. Let go, and it follows its true nature. Straight line inertia. This is Newton's first law in action, wrapped inside a spinning frame. An object in motion continues in a straight path, unless acted upon. Centripetal force is that action. It constantly nudges the object toward the center. And the faster you go, or the tighter the circle, the more centripetal force you need. That's why race cars hug wide turns at high speeds. And why astronauts on a centrifuge feel pressed into their seats. In physics, the formula for centripetal force is force equals mass times velocity squared, divided by radius. In words, the inward force required increases with the square of speed, and decreases with wider turns. This is why tighter spins feel more intense, why roller coasters feel heavier in tight loops, why planetary rings form where balance is just right. And yet, from the inside, circular motion feels like something is pushing you out. But there is no outward force. This feeling is a result of inertia. Your body wants to keep going straight, and the curve pushes back. That outward sensation is called centrifugal force. But it's not a real force. It's a frame of reference illusion. In a rotating frame, you feel flung out. But in reality, there is only the pull inward. If you spin a bucket of water fast enough, the water stays in, not because something is pushing it up, but because the bucket keeps turning and pressing it in a circle. From the water's perspective, nothing's holding it. But from our frame, we see the circular force, the constant inward pull that keeps it from spilling. This same principle governs washing machines, satellites, and even your inner ear. When your semicircular canals detect acceleration, they're registering the tug of centripetal force. Your brain turns that into balance. And when that balance is off, you get dizzy, because your inner sensors and your body's motion no longer match. It's your body reminding you that motion is always a negotiation between inertia, force, and perception. Centripetal motion is also what gives structure to galaxies. Stars orbiting a center, dust whirling into spirals, planets holding moons. Moons raising tides. All of it. A cascade of turning paths. All of it, shaped by forces pulling inward while motion resists outward. A balance. A circle. A compromise. This compromise plays out everywhere. In traffic roundabouts. In amusement park rides. In the whir of fans. The spin of hard drives. The rings of Saturn. Even atoms. Electrons move in probability clouds, but their motion is still governed by forces that pull them toward the nucleus. And in particle accelerators, massive magnets curve particles into circular paths at near light speeds. The same principle, different scale. That's the beauty of Newtonian mechanics. It scales. It explains the loop of your lasso and the orbit of your moon, the carousel and the cyclotron. The circle is the same, only the context changes. Even biological systems use circular motion. Blood flowing through arteries, curves with each heartbeat. Weather systems form rotating cyclones and anticyclones due to the Coriolis effect, another byproduct of circular motion on a rotating Earth. And consider artificial gravity in space. By rotating a habitat, engineers simulate gravity through centripetal force, spin the cylinder, and people inside are pressed to the outer walls. Not by gravity, but by inertia, countered by a manufactured centripetal pull. This is what future space colonies may use. A spinning world, where walking feels normal, even in the vacuum of space. Circular motion is not a novelty. It is a foundation, a physical truth that shapes wheels, orbits, storms, machines and lives. We live on a spinning sphere. We orbit a star. Our galaxy rotates slowly, and every one of those curves, every loop of motion is balanced by a force pulling in, the force that keeps chaos from breaking loose. Wherever there's a curve, there is a force, and wherever something turns, Newton is present. This is circular motion. It is not motion lost, it is motion guided, bent, redirected, controlled, a never-ending fall toward a center that is never reached. Like gravity's handshake with motion. A curve that loops forever, and a force that says, stay close or fly away. Imagine a hill. Not too steep, just enough to make something roll. Place a block at the top, let go, and down it goes, but not because you pushed it, because gravity did, and the slope let gravity show off. This is the power of the inclined plane. It's not a machine in the way we think of engines or gears. It's a surface, a tilt, and that tilt changes everything. An inclined plane is one of the 6 classical simple machines. It trades force for distance. It lets you lift something heavy, not by brute strength but by strategy. Instead of lifting straight up, you slide along an angle. You still do the same work, but the effort feels easier, because the force is spread over a longer path. This is Newton's playground. Force, mass, acceleration, all reshaped by slope. Let's say you want to push a crate up a ramp. Straight up would take enormous force equal to the crate's weight. But with a ramp, that force is split. Part of it fights gravity. Part of it is wasted to friction. But most importantly, it's manageable. You can do more with less, as long as you're willing to go farther. The trade-off is always the same. Less force, more distance. More force, less distance. This is the principle of mechanical advantage. The inclined plane spreads out the force you need over the length of the ramp. The steeper the ramp, the more force you need. The shallower the ramp, the longer it gets. But the easier the push. There's a formula behind it. Mechanical advantage equals the length of the slope divided by its height. So a ramp twice as long as it is high cuts the effort in half. This is why ancient builders used ramps to construct temples and pyramids. Not because they lacked power, but because they understood physics. They knew how to extend a force to make it gentler. And you use the same logic every time you walk up a ramp instead of stairs. It feels easier, not because gravity changed, but because your path did. Inclined planes show up everywhere. Wheelchair ramps, loading docks, slides at the playground, highway on-ramps, mountain roads winding back and forth. All of them are strategies. They take a vertical challenge and turn it into a manageable incline. And in every one, Newton's laws operate behind the scenes. Let's break it down further. When an object sits on a ramp, gravity pulls it down. But because the surface is tilted, gravity splits. One part pulls the object into the ramp. That's the normal force. The other pulls it down the slope. That's what causes motion. This component is why a block slides on an incline, and why it stays still if friction balances it. Add more tilt. The downslope force grows. Reduce friction. And now it moves. There's a tipping point, literally, where motion begins. It's the moment friction can't hold back gravity's invitation. This is the beauty of physics in angles. The very shape of a surface changes the motion on it. And when we bring pulleys into the picture, things get even more interesting. A pulley is another simple machine. It redirects force. Attach a rope over a wheel and pull down, the object goes up. You don't change the amount of force needed, but you change the direction you apply it. Add more pulleys, and you reduce the effort too. Like ramps, pulleys use mechanical advantage. They're inclined planes, wrapped in circles. A fixed pulley changes direction. A movable pulley halves the force. Combine them into a block and tackle system, and you can lift the world, or at least a car engine. This is what cranes use, what sailboats rely on, what elevators and hoists and theatre curtains all employ. They multiply your effort. They conserve energy. They obey Newton. And then there are wedges. A wedge is an inclined plane turned sideways. A knife, an axe, a chisel. They concentrate force. Instead of spreading it out, they focus it. You push down, the wedge pushes apart. It splits wood. It pierces surfaces. It doesn't lessen effort. It redirects it with brutal precision. Even the zipper on your jacket uses wedges. Teeth glide together, because a slider applies angled force in both directions. It's engineering in miniature. Force, broken into parts. This is how Newtonian mechanics hides in everyday life. Not as equations on a board, but as tools in your hands. As ramps beneath your feet. As the wheelbarrow, the crowbar, the screwdriver. And beneath every tool is a principle. Change the path, change the effort, change the motion. Inclined planes don't make work disappear. They just make it possible. In manageable pieces, in slopes and curves and clever angles. And in that they echo Newton's deepest idea, that motion is not just about force, it's about how force is guided, how direction matters, how surface and angle can change what's possible. So when you see a child on a slide, a truck rolling up a ramp, a mountain road spiraling through switchbacks, know that you're watching Newton in motion. Force made smooth, effort transformed, through the simplest of shapes, a slanted surface, an inclined truth. And in that truth is power, enough to build pyramids, enough to lift civilization, enough to reshape what effort really means. For momentum is motion with memory. It's not just about movement, it's about how much movement wants to keep going. And Newton gave us the key to understanding it. Momentum is the product of mass and velocity. In words, that means how hard something hits depends on how much stuff is moving and how fast it's moving. Throw a ping pong ball and a bowling ball at the same speed. They move the same distance in the same time. But only one will leave a dent. That's momentum. Small object moving fast and have the same momentum as a large object moving slow. It's the combination that matters. Mass times velocity. A delicate object moving swiftly can strike with surprising power. A heavy one barely moving can still push with force. In physics, momentum is a vector. It has direction as well as magnitude. Change either, and the momentum changes. Think of a moving train. It's not just heavy, it's relentless, because of its momentum. To stop it, you need more than just brakes. You need time, distance, because momentum resists change. It's Newton's first law again. In a new outfit, an object in motion stays in motion unless acted on, and the more momentum it has, the harder it is to stop. Momentum isn't just a measure of effort. It's a promise. It tells us how much motion an object carries with it, how much it wants to keep going, and it's conserved. In a closed system, where no outside forces interfere, the total momentum before an event equals the total momentum after. That's Newtonian gold. Picture two ice skaters pushing off each other. They fly apart in opposite directions, not randomly, but predictably. Their total momentum stays the same. If one is heavier, the other flies off faster. If both are equal, they glide away symmetrically. This is conservation of momentum in action. It's elegant, reliable, and everywhere. Think of collisions. A moving car hits a parked one. The first slows down. The second starts moving. Some momentum was transferred. Some was absorbed. But total momentum, it remained steady. This is why car crashes are studied with momentum equations. Why sports scientists calculate impact force. Why space agencies design docking procedures with extreme precision. Because in collisions, Motion doesn't vanish, it moves. Momentum is also what keeps rockets stable. When engines fire, gases shoot backward. Rocket surges forward. Action, reaction, momentum changing forms, but never disappearing. And when rockets adjust direction, they don't fight gravity head-on. They change momentum. They pivot, nudge, glide into new paths. It's art, built on physics. Now add angular momentum. It's momentum, but spinning. A figure skater, twirling, pulls in her arms. She spins faster, not because she adds energy, but because she changes her shape. She conserves angular momentum. The smaller radius means faster spin, and the total spin mass times speed times radius stays the same. This is why ballerinas glide, why planets rotate, why neutron stars spin like cosmic drills after collapsing. Angular momentum is just as sacred, just as conserved, and just as beautiful. You see it in spinning wheels, gyroscopes, bicycles staying upright. The spinning object resists change to its orientation. That's angular momentum defending its path. Momentum also explains why things don't bounce forever, why rubber balls lose height, because momentum is shared, spread, converted into sound, into heat. Some goes back to motion, some doesn't. But it's not destroyed, it's redistributed. The system, all the pieces together, still obeys the rule. Total momentum remains. This is what lets physicists map explosions, reconstruct collisions, predict chain reactions. And it's not just science, it's everywhere. You feel momentum in your body every day. In the way your arms swing when you run, in the way a door resists when you try to stop it mid-swing. Momentum is why traffic feels heavy, why a punch lands harder when thrown mid-sprint, why a speeding bicycle is harder to steer. The more momentum something has, the more committed it is to its path. Even language borrows the term. We say projects have momentum. Movements gain it, because we understand, even unconsciously, that momentum is resistance to interruption, motion that prefers continuation. And that metaphor is grounded in real mechanics, in Newton's world, where motion is mass and speed, where inertia has direction, where force isn't just a push, but a consequence. Momentum gives us a way to see motion as a legacy, not a moment, but a carryover, a thread that connects before and after. And when we conserve it, we honor Newton's second and third laws. We acknowledge that in every exchange something remains. Push, recoil, hit, bounce, spin, sustain. It's not just motion, it's history and motion. Impulse is a whisper that becomes a shout. It's not the force alone, it's how long the force lasts. A brief push, a sudden strike, a change in momentum drawn out over time. This is impulse. It's the bridge between force and momentum. The moment when one becomes the other. Impulse equals force multiplied by time. That's the heart of it. A gentle push for a long time can do what a hard hit does in an instant. Push a door slowly and it swings open. Smack it fast, and it swings just as far, maybe farther. Same change in momentum, different delivery. Impulse is the package. Force and time are the ingredients. This idea is simple, but powerful. It's the reason seatbelts exist. The reason airbags save lives. The reason boxers train to roll with punches. Because time matters. How fast momentum changes can be the difference between safe and shattered. Imagine a car crash. Without a seatbelt, your body stops abruptly. All that momentum gone in a split second. But if the stop is stretched out by a belt, by an airbag, the force is less brutal. Same change in momentum. Longer time, lower force. Impulse is conserved, but the experience changes. This is Newton's second law, reimagined. Force equals mass times acceleration, and acceleration is the change in velocity over time. So rearranged, it tells us force times time equals mass times change in velocity. In other words, impulse equals change in momentum. Impulse is not just a burst, it's a transfer, motion handed off from one object to another. And the way it's handed off, the duration, the pressure, the contact, shapes everything. Think about sports. In baseball, the crack of the bat isn't just power, it's timing. The contact is brief, but the force is immense. In football, pads spread the force over time. In martial arts, a punch isn't about swinging wildly, It's about delivering maximum momentum in the shortest instant possible. Impulse is behind every swing, every pass, every bounce, every block. Even nature uses impulse. Raindrops hitting the ground transfer impulse to soil. Waves crashing against cliffs change rock over time. Meteorites transfer sudden enormous impulses that reshape landscapes. Impulse doesn't ask permission. It leaves a mark. It's Newton's language of sudden change. But impulse isn't just explosive, it's also delicate. Think of a child pushing a swing, each push small, each moment brief. But over time, momentum builds. The swing rises higher, not from a single force but from a collection of impulses, stacked, timed, repeated. This is resonance in disguise. Small pushes, if timed right, can move the world. Impulse choreographed. You can see this in how we walk. Every step is an impulse, a collision with the ground, a transfer of force over time. It's not violent, it's rhythmic, balanced. Your foot pushes. The ground pushes back. You move. Momentum changes subtly, smoothly, and impulse makes it happen. Drop an egg onto the floor and it shatters. Drop it onto a pillow and it bounces. Same egg, same mass, same downward momentum. But one stops suddenly, the other stops gently. Impulse is the same. Force is not, because time changed. This is the principle behind crumple zones in cars. They're not there to look pretty. They absorb momentum over time, convert force into harmless deformation, turn disaster into survivable delay. Impulse spreads the energy, dilutes the danger, extends the change. We also harness impulse in reverse. In rockets, engines fire for a short time, but the impulse is massive. That brief thrust changes momentum for the entire spacecraft. And in machines we modulate impulse with springs, dampers, buffers. In hammers we concentrate it. In shock absorbers, we extend it. Impulse is not fixed. It's flexible, shaped by design. In tools, in materials, in strategies. Impulse even shapes biology. Muscles contract quickly or slowly depending on need. Neurons fire in bursts. Micro-impulses guiding thought, action, reaction. Our bodies are tuned to manage momentum, to give and receive force over time, to survive change by softening impact. That's impulse at work. Not a brute. A strategist. In Newton's world, impulse is the hidden artist. It paints with contact, shapes motion with duration, sculpts change with care or violence, depending on time. Every time you catch a ball, every time you brake your bike, every time a diver hits the water and curves just right, impulse is there, modifying force, transforming impact, extending change. So next time you feel a bump, a shove, a sudden shift, don't just think force, think time, think impulse. Because in the dance between motion and stillness, it's not just how hard you push, it's how long you touch. And Newton knew that moment of contact changes everything forever. Impulse. The briefest push, the longest consequence. Where does something truly balance? Not just where it stands still, but where its mass says it should. That point, that silent pivot, is called the center of mass. And it is everywhere, in every object, in every motion, in every turn and fall and flight. It is the heart of Newton's silent geometry. The center of mass is the average position of all the mass in an object. Imagine every atom whispering where it sits, and the center of mass is the point where their voices cancel out. Pick up a hammer, balance it on your finger, you'll find one spot where it doesn't tip. Not the middle of the handle, not the head. Somewhere in between. That's its center of mass. A single invisible point that tells you how it moves. And that movement is what Newton cared about, because when forces act, they move mass. And that mass moves around its center. If you throw the hammer through the air, it tumbles. But watch closely. One point, the center of mass, traces a smooth arc. Everything else spins around it. That's not coincidence. That's law. Even chaotic motion has a simple line drawn through it. A balance hidden in the blur. The human body works the same. Your center of mass is usually near your pelvis. But bend over, raise a leg, extend an arm, and it shifts. Gymnasts, dancers and divers learn this instinctively. They feel where their center moves, and they control it. Like a pilot steers a plane, jump, flip, twist, the body moves, but the center follows a clean path. This is how motion becomes grace. The center of mass is not always inside an object. A hollow ring, a boomerang, a horseshoe. Their mass surrounds an empty space, and yet the center of mass still exists. Sometimes in air, sometimes in vacuum. It doesn't need matter. It needs balance. And Newton knew forces don't care about shape. They act on mass. They act on centers. Imagine two children on a seesaw, different weights, but place the heavier one closer to the center, and it balances. That's because the torque on both sides is equal. Mass times distance. And the pivot point, the fulcrum, becomes the axis of balance, the dynamic mirror of the center of mass. Even in play, physics rules. And the center watches quietly. When designing machines, center of mass matters. Top-heavy robots fall easily. Off-balance rockets tumble out of control. Vehicles skid or spin if their weight isn't centered correctly. Balance isn't optional. It's mechanical survival. And in sports, knowing where your mass is centered makes the difference between control and chaos. Between landing a jump or crashing hard, the center of mass determines stability. A wide stance lowers it. Spreading arms shifts it. Tucking in brings it closer to the core. That's why tightrope walkers use long poles. It lowers and widens their center of mass, gives them time to adjust, room to breathe, and less chance to fall. We also see this in spinning objects. A thrown disc, a flying arrow, a pirouetting ballerina. If the center of mass lines up with the axis of spin, the rotation is smooth. If it doesn't, wobble begins. Unbalanced washing machines, spinning tops that drift. Even Earth has a wobble. A slow precession caused by uneven mass and external tugs. Balance is never perfect. But the center always guides. In orbit, satellites spin with precision. Their center of mass is mapped and monitored. Even a slight imbalance could send them tumbling. Engineers use counterweights, adjustments, because in space, everything spins forever, unless corrected, and correction means controlling the center. It's why spacecraft dock slowly, why stations have gyroscopes, why precision is more than pride. It's safety. Because the farther you move from the center of mass, the more unpredictable motion becomes. Even atoms obey this rule. In molecules, the center of mass determines vibrational modes. The whole structure bends, stretches, rotates, all around this invisible core. And in collisions, whether billiard balls or subatomic particles, the center of mass frame simplifies everything. It's the view from which motion becomes symmetrical, where energy is easier to count, where chaos finds clarity. And it goes deeper. Earth and the Moon orbit a shared center of mass. Not the center of Earth, but a point inside it, slightly off-center. They dance in tandem. A dual spin. A relationship ruled not by size but by mass, and the Sun does the same with all its planets. The solar system doesn't orbit a perfect center. It shifts. It sways, because the center of mass floats with the balance of all bodies. The Sun moves too. In astrophysics, the barycenter, the system's center of mass, is how we detect hidden planets. Stars wobble. Light shifts. Not because we see the companion, but because we see the imbalance. The center reveals the unseen. It is both location and signal. Balance is never just about stillness. It's about predictability. If you know where the mass balances, you know how the object will move. You can plan, control, design. And if you miss that point, motion becomes mystery. Stability becomes gamble, and Newton's laws feel less like rules and more like consequences. Center of mass is not flashy. It's not loud. It doesn't glow or hum. But it's the quiet boss of every movement. Every object has one. Every throw revolves around one. Every leap, every fall, every graceful arc, guided by a point with no shape, but infinite meaning. It is the anchor of motion, the compass of control, the true center of everything that moves. Rotation is a different kind of motion. It spins. It twirls. It loops. And while it feels familiar, a wheel turning, a planet orbiting, a child spinning in a chair, the physics behind it is a distinct world. Linear motion is about straight lines. Rotational motion is about circles. And Newton's laws still apply, but they speak a different dialect here. In this chapter we step off the line and enter the spin. We enter the world of rotational motion. Imagine a merry-go-round. Children at the edge are flying past faster than those near the center, but they all complete one revolution in the same time. This is the difference between angular velocity and linear velocity. Angular velocity is how quickly something spins, measured in degrees or radians per second. Linear velocity is how fast a point on that object moves through space. Points farther from the center move faster, because they cover more ground in the same time. This is why the tips of a wind turbine blade move faster than the base, why the outer edge of a vinyl record travels farther than the label. It's the radius that makes the difference. Velocity equals angular speed times radius, so the farther out you go, the faster you move. Even when the spin is constant. That's rotational motion. Simple in concept, deep in effect. Just as mass resists change in linear motion, rotational motion has its own resistance. It's called rotational inertia, also known as the moment of inertia. It depends not just on how much mass an object has, but where that mass is located. Spread it out, and it resists rotation more. Bring it close to the axis, and it spins easily. This is why figure skaters pull in their arms. Why spinning chairs move faster when you curl up. You're reducing your moment of inertia. And to conserve angular momentum, your spin speeds up. It's not magic. It's mechanics. Angular momentum is the rotational twin of linear momentum. It's the product of rotational inertia and angular velocity, and it's conserved. If no external torque acts on a system, its angular momentum remains constant. This is why the Earth keeps spinning. Why gyroscopes hold their orientation. Why a spinning satellite in space doesn't stop. No friction, no resistance, no change. Just infinite spin. Torque is the force that causes rotation. Push a door near the hinge, it's hard. Push it at the edge, it swings. Same force, different effect. Torque equals force times the distance from the pivot point. The farther out you push, the more torque you generate. This is why wrenches have long handles, why crowbars are curved, why livers were celebrated by Archimedes. Because force, multiplied by distance, creates rotation. Rotational motion also includes angular acceleration, the change in angular velocity over time. Like linear acceleration, it depends on torque and inertia. More torque means faster acceleration. More inertia means slower response. This is how engines revise, how wheels spin up, how storms rotate. A torque is applied, and rotation grows. We can even describe kinetic energy in rotation. It's not just mass and speed now. It's 1/2 times the moment of inertia times angular velocity squared. So a spinning object holds energy. A flywheel, a rotor, a spinning disc. They all store motion. They all resist change. And when that motion stops, the energy must go somewhere, into brakes, into heat, into sound. Nothing disappears. Rotational motion is everywhere. It's in the Earth's spin, the moon's orbit, the wheels of your bike, the arms of a windmill. It's in every engine, every gear, every spinning top. It even shapes weather. Coriolis forces, born from Earth's rotation, curve winds into hurricanes. And it governs galaxies. Stars swirl in spirals because of the same principles. Mass, radius, velocity, bound in a cosmic dance. Even time can bend to rotation. Einstein's relativity predicts that rotation can affect the passage of time. In extreme cases, such as near black holes, rotational motion warps the fabric of spacetime. And yet, the rules remain grounded. Angular velocity, torque, moment of inertia, they still apply. When you stir a cup of coffee, you're applying torque. When a turbine spins from steam pressure, it converts linear force into rotational energy. When a child spins on a playground disc and throws out their arms, they change their moment of inertia and feel the change. It's Newton in circles. Gravity and force, playing on a loop. And at the center, always is balance. A pivot, a core that everything spins around. In the lab, we use rotational motion to study systems from gyroscopes to planetary models. In engineering, we use it to design motors, turbines, engines. In daily life, we use it without knowing, turning knobs, twisting caps, riding wheels. Rotation is second nature. And yet, its physics is a world of its own. Newton's laws didn't stop at straight lines. They curved, they spun, they adapted. And in doing so, they gave us the tools to understand a world in motion. All of it. Even when it spins. So next time you see a wheel turning, a planet rotating, or a child spinning for joy, know that you're watching laws in action. Circular, predictable, endlessly profound. That's rotational motion. Newton knew it. And now, so do you. There's a twist in the story of motion. A special kind of force. One that doesn't push or pull in a straight line, but causes things to rotate. That twist is called torque. And torque is to rotation what force is to linear motion. Push a wheel at the center, and it barely moves. Push at the edge, and it spins. That's torque. A force with leverage. A turning influence. Torque is calculated by multiplying force by the distance from the axis of rotation. The farther you apply the force from the pivot, the more torque you generate. This is why we use long-handled wrenches. Why crowbars are shaped the way they are. Why a door opens easily when pushed at the handle, and stubbornly if you push near the hinge. Torque isn't just about how hard you push, it's where you push. That leverage is everything. The formula for torque is torque equals force times radius times the sine of the angle between them. But in everyday cases, when force is perpendicular to the lever arm, it's simply force times distance. This means torque has direction. It can be clockwise or counterclockwise, just like rotational motion. And it follows the right-hand rule. Point your thumb in the direction of the axis. Curl your fingers in the direction of rotation. That's torque's direction. It's a vector, not just a number. And this direction matters. When two torques act in opposite directions, they can cancel out, or create net rotation, or hold a system in balance. This is how balance beams, seesaws, and levers work. It's the silent conversation of torque. Consider a mobile hanging from the ceiling, delicate arms balanced with objects on either side. Different masses, but placed at different distances, and they stay perfectly still, because the torques are equal and opposite. This balance is how architects design buildings, how cranes lift loads without tipping, how bridges distribute stress. It's not brute force, it's elegant torque management. Even animals use torque. When you throw a punch, kick, or leap, your body generates torque. Your muscles apply force away from your joints. Bones become levers, and every movement becomes rotational. The human body is a machine of torque. Each joint, a pivot. Each muscle, a motor. Each motion, a story of rotation. And Newton wrote the rules. When torque is applied to an object with rotational inertia, it causes angular acceleration. This is Newton's second law for rotation. Torque equals moment of inertia times angular acceleration. It's the rotational twin of F equals m times a. Force changes velocity. Torque changes spin, and the more rotational inertia, the harder it is to change. This is why heavy machinery takes time to speed up, why large flywheels resist sudden change, why spacecraft use reaction wheels to turn slowly and precisely. And when torque stops, spin stops, but not instantly. Momentum carries on, until resistance, usually friction, brings it to a halt, or until equal torque in the opposite direction cancels it out. That's balance again. Torque even shapes nature. When tectonic plates grind and build tension, they store rotational stress. When they slip, earthquakes happen. Energy is released in a twist. The Earth shakes not just from pressure, but from torque unleashed. In weather systems, torque creates cyclones. Warm air rises. The planet spins. Rotation begins. Storms are torque in action on a planetary scale. And in technology, torque defines design. From engine output to wrench efficiency. From servo motors in robotics to electric bikes. Torque is not just power. It's usable, rotational force. Every gear, every motor, every tool is engineered to optimize torque. And every spin you feel, every twist you control, every lever you pull, is a conversation with torque. It whispers in every rotation. And torque can be deceptive. More torque doesn't always mean more speed. High torque gives strength, the power to turn, but that power can come at low speed. Just like a truck climbing a hill. Torque lets it pull, not fly. In engines, torque and horsepower are two sides of the same coin. Torque moves, Horsepower sustains, one begins, the other continues. So engineers match torque to purpose, high torque for lifting, high speed for racing. And in between, a balance, a compromise tuned for performance. We even feel torque in reverse. When you over-torque a bolt, it snaps. When you twist too far, things tear. It's the edge of force, made rotational, and torque doesn't just move things, it breaks them too. That's why precision matters. Torque wrenches, torque specs, tools that measure rotation down to the click, so nothing fails. And in all this, in every design, every twist, every calculation, Newton sits quietly, smiling. Because torque was always part of the story, we just had to spin around to see it. So, the next time you turn a handle, open a jar, twist a key, or spin a screw, you're not just using your hands, you're wielding torque. The twist that turns the world. The force that spins, the lever's secret. Newton's quiet gear. That's torque. And now, it's in your hands. Spin something. Anything. A coin, a top, a wheel. Watch it turn. Now try to stop it, suddenly, sharply. It fights back. That fight, that stubbornness to stop spinning, is angular momentum. And angular momentum is motion's commitment to its own rotation. It's not just how fast something spins, it's how much it wants to keep spinning. In linear motion, momentum is mass times velocity. In rotation, angular momentum is moment of inertia times angular velocity, but there's more to it. It's also direction. Angular momentum points along the axis of rotation. It doesn't just measure how much, it points to where. And it's conserved. In a closed system, where no external torques act, angular momentum remains constant. It doesn't fade. It doesn't disappear. It persists. Watch a figure skater spin. Arms stretched wide. The spin is slow. Arms pulled in. The spin accelerates. Why? Because when mass moves closer to the axis, the moment of inertia drops. To conserve angular momentum, the spin rate increases. It's Newton's rules at play. Rotation reshaping itself without losing its essence. You see this in planets, in neutron stars, in tornadoes and whirlpools and hurricanes. Every time mass spirals inward, rotation speeds up. Angular momentum conserved, shape changed, speed adjusted. This is why stars collapsing into neutron stars spin so fast. Their size shrinks, their spin explodes. They become cosmic tops rotating dozens of times per second. It's not added energy, it's angular momentum compressed. Stored motion intensified. Even satellites use this. Gyroscopes hold orientation. Reaction wheels shift, spin without burning fuel. They don't push, they twist. One part turns one way, the other reacts the opposite. System conserved. Direction changed. In zero gravity this is gold. Momentum is motion's currency, and angular momentum is its rotational form. Spin a bike wheel, and hold it by the axle. Now tilt it. Feel the resistance. That's angular momentum fighting to maintain its orientation. It doesn't want to turn in a new direction. It wants to spin as it was. This is why gyroscopes resist motion. Why spinning tops stay upright. Why balance becomes easier when motion is circular. Angular momentum defends its path. Like a compass that remembers. And it's not just in play or space. It's in atoms. Electrons have angular momentum. They orbit. They spin. Their orientation matters. It defines energy levels. It dictates magnetic properties. Quantum angular momentum, called spin, is one of the most fundamental properties of particles. It cannot be changed. It's quantized. It's angular momentum on the smallest scale. At every level of reality, angular momentum matters. It shapes structure. From galaxies to gyroscopes, from neutron stars to electrons. It makes sense of orbits, of rotations, of the way things resist change. Because to change angular momentum you need torque, a twist, a force. Without it, the spin stays, unbroken, untouched, unchanged. This is why we harness it, why we trust it, why spinning systems are stable. You can see it in ice skaters, in divers twisting mid-air, in dancers pivoting on toes. They all use angular momentum, not just to move, but to control movement. Pull in, extend out, turn faster, slow down, manipulating inertia to match the moment. It's Newton, in rhythm. You can even feel it when you spin in a chair, hold weights in your hands, arms extended, spin, then pull the weights in. Your speed increases. No one pushed you, but your moment of inertia shrank, and angular momentum kept its promise. Spin fast to match the mass. It's not magic, it's physics. And it's beautiful. We build machines on this principle. Flywheels that store energy, wheels that balance motion, gyroscopes in planes, in phones, even in VR headsets. We depend on angular momentum without seeing it, but it's always there. Keeping things upright, making motion predictable, holding balance without strings. Even in orbit, spacecraft rotate to aim instruments, to communicate, to adjust. Not with thrusters but with internal wheels, spinning one way, rebalancing the other, momentum conserved. Path corrected. It's silent, it's subtle, it's precise, and it's Newtonian to the core. So next time you spin something, a toy, a tool, a thought, remember what keeps it going, what holds it steady, what guards its direction like a secret. It's not just motion, it's angular momentum, the spin that stays, the whisper of rotation, the law that resists change until you twist hard enough. It's not just science, it's motion's promise, a commitment written in circles, a legacy of turning that won't let go. That's angular momentum, and it's everywhere, forever spinning. Let's talk about effort, about how force gets applied, and how it moves something. This isn't about just having power, it's about making that power do something. This is where we meet a concept so simple, yet so central: work. Work is force over distance. When you apply a force to something, and it moves in the direction of that force, you've done work. Push a box across the floor, lift a bag onto a shelf, throw a stone across a river. Each of those involves force. Each of those involves motion. That's work. And Newton would be nodding. In physics, work has a clear, specific meaning. It's not effort alone. It's not how tired you feel. It's calculated. Force multiplied by the distance moved in the direction of that force. So if you push hard but nothing moves, no work is done. If you lift something straight up and it moves vertically, work is done. If you carry something across a room without lifting or lowering it, you're holding force, but doing no work in the physics sense, because the movement wasn't in the direction of the applied force. This clarity matters. It separates energy from exertion, and it gives us tools to measure real change. Work is measured in joules. 1 joule is 1 Newton of force applied over 1 meter. It's a small amount, but it adds up, because all motion, all physical change, comes from work. Imagine lifting a book. Gravity pulls it down. You apply force upward. If the book rises, you've done work against gravity. That energy goes somewhere, into the book's position. Its potential energy increases. Now imagine you drop it. It falls. Potential becomes kinetic. Stored energy turns into motion. The work you did lifting the book becomes the motion it gains while falling. Work is the transaction, energy is the currency. And when you push an object horizontally, friction fights you. You apply force. You do work, but some energy becomes heat. Some becomes sound. Some becomes deformation. Work isn't always efficient, but it always leaves a trace. In mechanics, we can track it, because the work energy principle tells us something powerful. The net work done on an object is equal to its change in kinetic energy. If an object speeds up, work was done. If it slows down, work was done against it. This links Newton's second law to energy. Force causes acceleration. Acceleration changes velocity. Velocity squared, that's kinetic energy. It all loops back. Work creates motion. Motion means energy. Energy tells us how much change occurred. And work is how that change gets written. Think about machines, levers, ramps, pulleys. All simple machines exist to do one thing: make work easier. Not by reducing the total amount of work, but by spreading it, changing the force, changing the distance. Less force, longer path. More force, shorter path. But the product, force times distance, remains. That's the work. It stays constant. Machines don't cheat work, they reshape it. This is why energy conservation matters. When you burn fuel, when you use electricity, when your muscles contract, you're converting energy into work. And that work moves things, changes things, builds, breaks, begins. It's also why engineers study work. Because lifting a load, launching a rocket, running a turbine, it's all about how much work you can extract from a given source of energy. Work turns energy into motion, and energy into results. It's not abstract, it's real. Climb a hill, and your muscles do work. Gravity resists. Friction adds to the toll. But every step raises your potential energy. And that energy came from fuel, food, digestion, chemistry. Work connects biology to physics, calories to motion, effort to elevation. And even when you rest, work lingers. The stored energy in a spring, the tension in a bow, the height of a perched boulder, all results of past work, all waiting to be released. That's the power of work. It leaves the world changed. No force, no movement, no work. Force with motion. That's transformation. That's what physics tracks. Not just effort, but outcome. So whether it's building pyramids, or charging your phone, or biking up a hill, work is happening. Force, distance, direction, and every time those align, the world shifts. Energy flows. Motion begins. That's not metaphor, it's Newton. It's real. It's work. Let's talk about the fuel that drives everything. Not just motion, not just heat, everything. That fuel is energy. And it comes in many forms. But the story starts with two, potential and kinetic. Energy is the currency of the universe. It's what makes change happen. It doesn't disappear. It doesn't get created from nothing. It transforms when you climb a hill. Your body stores energy in elevation. That's potential. When you run down, that energy becomes speed. That's kinetic. Two sides of the same coin. One waiting, one moving. Potential energy is stored energy. It's energy of position. Lift a ball, wind a spring, compress a rubber band. You're putting energy into it, storing it, like winding a watch. The higher the ball, the more potential. The tighter the spring, the more tension. This energy doesn't vanish. It waits. Quiet. Ready to become motion. And when it does, when the ball drops, the spring uncoils, it becomes kinetic. Energy of motion. Kinetic energy is moving mass. It's action. The faster something moves, the more kinetic energy it has, and it grows fast. Kinetic energy is proportional to velocity squared. So doubling speed gives you 4 times the energy. This is why crashes are so violent at high speeds. Why a bullet has so much punch. Why falling from a taller height is so much worse. Speed adds energy fast, and Newton's laws are right there, tracking every joule. Energy can't be seen directly, but you can feel it. You can see its effects. A moving car, a burning fire, a spinning wheel. All expressions of energy, and it never gets lost. Only changed. That's the first law of thermodynamics. Energy cannot be created or destroyed, only transformed. From potential to kinetic, from chemical to mechanical, from electrical to thermal. This principle is the bedrock of physics. It's what keeps the universe honest. Think about a roller coaster. At the top, full of potential energy. As it drops, energy shifts into kinetic. As it climbs again, kinetic turns back into potential. And friction, that turns some of it into heat. But nothing vanishes. The total energy remains. It just moves around, like money passing through hands. It changes forms, but it's all accounted for. We use this principle everywhere. In engines, in batteries, in our bodies. Calories are chemical energy. They become kinetic energy when you run, heat energy when you shiver, electrical energy in your nerves. Everything you do, every breath, blink or beat, runs on energy transformations, and every transformation obeys the same rule. Energy in equals energy out. Even at rest, objects have energy. A stretched bow, a compressed spring, a charged battery. All waiting to release. All holding stored power. Potential energy with a purpose. And when that energy is released, it becomes kinetic. It moves an arrow, turns a motor, heats a wire, drives a process. It's a chain reaction of form and function. But energy doesn't just come from height or speed. There's chemical energy in bonds, nuclear energy in atoms, thermal energy in heat, electrical energy in charge. Every form is just a different costume for the same actor. Energy, shape-shifting, conserve, following rules we can trust. And those rules allow us to build, to design, to power entire worlds. Because energy is predictable. We can calculate it, measure it, convert it, balance it. When we build a dam, we store potential energy in water. When we release it, turbines spin. Kinetic energy becomes electrical energy. That electricity travels to homes where it becomes heat, light, or sound. And the cycle continues. Long after the switch is flipped, energy still flows, changing form, never lost. That's why efficiency matters. Some energy always turns into heat, or sound, or friction. Useful energy becomes less useful. But the total still exists. It just spreads out, becomes harder to harness. This is entropy, the second law of thermodynamics, a whisper of order unraveling. But the energy, still there, still conserved, still shaping the world, from lightning to lasers, from rockets to radio waves, from the warmth in your hands to the core of the earth. Energy flows through everything, and Newton's mechanics give us the keys to ride that flow, to predict it, to use it. So when you lift, when you run, when you light a candle, or charge a phone, remember, you're not creating power, you're moving it, transforming it, respecting the laws that govern it. This is energy, the currency that never burns out, the lifeblood of motion, the reason work matters, the story behind every action. And it's not just theory, it's everywhere, it's real, it's conserved, it's energy, and it never stops working, ever. Ooh. Let's begin with a bold statement. In the universe, nothing is truly lost. Not effort, not energy, not even the faintest whisper of heat. Everything moves, everything shifts, but the total always remains. This is the conservation of energy. One of the most powerful laws in physics, one of the most trustworthy, one of the most universal. Energy can change forms, but it cannot disappear. It cannot be created from nothing, and it cannot be destroyed. It's a rule that gives structure to motion, and it's why physics works so well. Imagine a pendulum. At its highest point, all its energy is potential. As it swings down, that potential converts to kinetic. At the bottom it's moving fastest, all kinetic. Then it rises again. Kinetic becomes potential. Back and forth. No energy is lost. It just moves between forms, and unless friction or air resistance interferes, that pendulum would swing forever. But of course, real life isn't perfect. In reality, a little energy gets siphoned off. To sound, to heat, to the friction of the pivot. But even those aren't losses in the grand sense. They're just conversions. The total energy potential, kinetic, thermal, sound, still adds up. Always. This is the promise of conservation. This principle is at the core of all mechanics. When you fire a cannonball, the chemical energy in the gunpowder becomes kinetic. When you charge your phone, chemical energy from the battery becomes electrical. That electricity becomes light, sound, heat, and all those outputs, if measured properly, would match the input. No missing pieces, no mysteries, just energy changing shape. And following rules, this is how we power cities, how we launch rockets, how we design engines and bridges and electrical grids. We track energy, we calculate what's needed, we measure what's gained. And because energy is conserved, the math always balances. That's why engineers trust it, why physicists build on it, why you can count on it, even in the most chaotic systems. It's not just reliable, it's beautiful. Take a car going uphill. The engine does work. Gasoline's chemical energy converts into motion. Motion lifts the car. Kinetic energy becomes potential energy. Then, coming down, gravity takes over. Potential energy turns back into kinetic. Some becomes heat in the brakes. Some becomes sound. All of it adds up. Energy never leaves the equation. It only transforms. That's the genius of conservation. It gives us accounting for the cosmos, a way to track the invisible, a way to trust what we cannot see. Even when systems grow large, when planets orbit stars or galaxies spin in clusters, conservation of energy still holds. The math gets more complex, but the rule never breaks. And on the tiniest scale, atoms colliding, particles zipping through accelerators, the principle still reigns. Energy in equals energy out. No exceptions. It's as if the universe is keeping perfect books. No matter how much chaos you throw into the system, the balance holds. This is why roller coasters are designed based on conservation. You can predict how fast a cart will go at any point, based on height, based on gravity, based on friction. Because you're never guessing how much energy there is, you're just calculating where it moved, how it changed. And this gives us control. It gives us precision. It lets us shape motion, engineer experience, design reality. From thrill rides to power plants, even in your own body, the principle holds. You eat food, chemical energy. Your cells convert it to motion, to warmth, to thought. Your body becomes a moving system, a warm engine. Energy flows, nothing wasted, nothing lost, just a cascade of transformations, all measurable, all traceable. Conservation is also what helps us define closed systems. A closed system is one where energy doesn't enter or leave. Everything happens inside. Like a sealed container, like an ideal experiment. In such a system, energy transformations occur, but the total never changes. This lets us simulate the universe in labs, run models, test ideas, because conservation is constant, and constants are gold. When we study combustion engines, we map how energy moves, from fuel to explosion, from explosion to piston, from piston to wheels, from wheels to road. Each step has energy input and energy output. We track losses, we improve design, we get better, not because we're guessing, but because we're following the trail of conserved energy. Everywhere it goes, we follow people. Even in space, energy conservation helps us predict trajectories, launch speeds, orbital paths. When a spacecraft uses a gravity assist, it trades energy with a planet's motion. No energy is created, just redirected, rebalanced, and this lets tiny satellites reach the outer solar system. Because we understand the rules, and the rules reward clarity. Conservation doesn't make energy free, but it makes energy fair, predictable, accountable. So when you hear someone say energy is lost, know that it's not true. It's just changed, dissipated, converted, maybe into forms we don't use efficiently, like unwanted heat. But it's still there, still in the system, still adding up. This is how stars shine, how the sun gives warmth, how fusion balances pressure. Energy flows outward, light, heat, radiation, and at every step conservation governs it. Quietly, rigorously, without exception. It's law, not suggestion. So, the next time something moves, remember what made it move, the energy it carried, the transformations it passed through, the story it left behind, and know that the total never changed. It was just reshaped, bent, shared, but never lost. That's the conservation of energy. That's Newton's world. And we live in it. Every moment. There's a twist in the story of motion. A special kind of force. One that doesn't push or pull in a straight line, but causes things to rotate. That twist is called torque. And torque is to rotation what force is to linear motion. Push a wheel at the center, and it barely moves. Push at the edge, and it spins. That's torque. A force with leverage, a turning influence. Torque is calculated by multiplying force by the distance from the axis of rotation. The farther you apply the force from the pivot, the more torque you generate. This is why we use long-handled wrenches, why crowbars are shaped the way they are, why a door opens easily when pushed at the handle, and stubbornly if you push near the hinge. Torque isn't just about how hard you push, it's where you push. that leverages everything. The formula for torque is torque equals force times radius times the sine of the angle between them. But in everyday cases, when force is perpendicular to the lever arm, it's simply force times distance. This means torque has direction. It can be clockwise or counterclockwise, just like rotational motion. And it follows the right-hand rule. Point your thumb in the direction of the axis. Curl your fingers in the direction of rotation. That's torque's direction. It's a vector, not just a number. And this direction matters. When two torques act in opposite directions, they can cancel out, or create net rotation, or hold a system in balance. This is how balance beams, seesaws, and levers work. It's the silent conversation of torque. Consider a mobile hanging from the ceiling, delicate arms balanced with objects on either side. Different masses, but placed at different distances, and they stay perfectly still, because the torques are equal and opposite. This balance is how architects design buildings, how cranes lift loads without tipping, how bridges distribute stress. It's not brute force, it's elegant torque management. Even animals use torque. When you throw a punch, kick, or leap, your body generates torque. Your muscles apply force away from your joints. Bones become levers, and every movement becomes rotational. The human body is a machine of torque. Each joint, a pivot. Each muscle, a motor. Each motion, a story of rotation. And Newton wrote the rules. When torque is applied to an object with rotational inertia, it causes angular acceleration. This is Newton's second law for rotation. Torque equals moment of inertia times angular acceleration. It's the rotational twin of F equals m times a. Force changes velocity. Torque changes spin, and the more rotational inertia, the harder it is to change. This is why heavy machinery takes time to speed up, why large flywheels resist sudden change, why spacecraft use reaction wheels to turn slowly and precisely. And when torque stops, spin stops, but not instantly. Momentum carries on, until resistance, usually friction, brings it to a halt, or until equal torque in the opposite direction cancels it out. That's balance again. Torque even shapes nature. When tectonic plates grind and build tension, they store rotational stress. When they slip, earthquakes happen. Energy is released in a twist. The Earth shakes not just from pressure, but from torque unleashed. In weather systems, torque creates cyclones. Warm air rises. The planet spins. Rotation begins. Storms are torque in action on a planetary scale. And in technology, torque defines design. From engine output to wrench efficiency. From servo motors in robotics to electric bikes. Torque is not just power. It's usable, rotational force. Every gear, every motor, every tool is engineered to optimize torque. And every spin you feel, every twist you control, every lever you pull, is a conversation with torque. It whispers in every rotation. And torque can be deceptive. More torque doesn't always mean more speed. High torque gives strength, the power to turn, but that power can come at low speed. Just like a truck climbing a hill. Torque lets it pull, not fly. In engines, torque and horsepower are two sides of the same coin. Torque moves, horsepower sustains. One begins. The other continues. So engineers match torque to purpose. High torque for lifting. High speed for racing. And in between, a balance. A compromise tuned for performance. We even feel torque in reverse. When you over-torque a bolt, it snaps. When you twist too far, things tear. It's the edge of force, made rotational, and torque doesn't just move things, it breaks them too. That's why precision matters. Torque wrenches, torque specs, tools that measure rotation down to the click, so nothing fails. And in all this, in every design, every twist, every calculation, Newton sits quietly, smiling. Because torque was always part of the story. We just had to spin around to see it. So, the next time you turn a handle, open a jar, twist a key, or spin a screw, you're not just using your hands, you're wielding torque. The twist that turns the world. The force that spins, the lever's secret. Newton's quiet gear. That's torque. And now, it's in your hands. There's a rhythm in nature. A pattern of back and forth, of push and pull, of motion that repeats. You see it in a swinging pendulum, in a vibrating guitar string, in the way a child rocks back and forth on a swing. This is harmonic motion, and it's one of the most elegant forms of movement in physics. A dance between force and motion, between energy stored and energy released, between inertia and restoration. Harmonic motion happens when a system experiences a restoring force proportional to its displacement. In simpler terms, the farther it moves from center, the harder it gets pulled back. This pull, this balance, creates motion that's smooth, regular, and predictable, like a clock's pendulum, like a spring bouncing up and down, like sound waves traveling through air. Let's take the simplest example, a mass on a spring. Pull it down, let go. The mass rises, overshoots the rest point, and then falls again, over and over. The spring provides the restoring force, the mass provides the inertia, and together they create a loop of motion, a cycle, a harmony. The force pulling it back is described by Hooke's law. Force equals negative k times x, where k is the spring constant, and x is the displacement from the equilibrium. The negative means the force always pulls back towards center. The farther you stretch, the harder it pulls. This results in simple harmonic motion, where position, velocity, and acceleration all change in a sinusoidal pattern. That means they follow the shape of a sine wave, smooth, flowing, continuous. The position of the object oscillates around the center. Velocity peaks as it passes through the center. Acceleration peaks at the edges. Energy shifts between kinetic and potential, but the total energy stays the same, just like the conservation principles we already know. Now imagine a pendulum. The motion is slightly more complex than a spring, but still follows similar principles. Gravity provides the restoring force, inertia carries it forward, and the swing continues. As it rises, it slows. At the top, potential energy is highest. As it falls, speed increases. At the bottom, kinetic energy is highest, and the rhythm continues. A perfect trade-off between two kinds of energy. An endless cycle, if nothing interferes. But in the real world, something always interferes. Air resistance, friction, internal damping. These cause energy to slowly bleed from the system, and motion fades. This is where we shift from ideal harmonic motion to damped harmonic motion. Still rhythmic, still oscillating, but fading with time. The peaks get smaller, the motion softens, until finally it rests. This happens everywhere. In the vibrations of a tuning fork, in the springs of a car suspension, in the bounce of a basketball. Oscillations happen and fade. Energy dissipates, motion slows, but the rules stay the same. The math still works. The elegance of harmonic motion gives us predictability. Engineers use it to design buildings that withstand earthquakes. Musicians use it to tune instruments. Physicists use it to understand waves. Because at its core, harmonic motion is the foundation of wave behavior. Sound is a wave. Light is a wave. Even quantum particles can exhibit wave-like properties, and all those waves have roots in this principle. Now, let's talk frequency. The number of cycles per second, measured in hertz. A pendulum has a low frequency. A tuning fork, high frequency. Frequency determines pitch in sound, color in light, vibration in machines. And then there's amplitude, the maximum displacement from the center. Higher amplitude means more energy. A louder sound, a brighter light, a stronger shape. These two, frequency and amplitude, define the character of harmonic motion. But they're not completely independent. In many systems, mass and stiffness determine frequency. Heavier mass, lower frequency. Stronger spring, higher frequency. This is why a larger bell rings deeper. Why a small string vibrates faster. Why heavy machines move slower. The math is clear. The square root of spring constant divided by mass. That's how you find natural frequency. And every system has one, its own beat, its own rhythm, its own voice. And when you strike it, it responds. That's the beauty of harmonic motion. It shows us the balance between motion and memory, between push and pull, between what moves and what restores. And it's everywhere. From molecules vibrating, to buildings swaying, to planets tugged by unseen companions. all responding to some force, some displacement, some return to center. Even your heart beats in rhythm. Even your voice vibrates with harmonic overtones. Even the earth itself rings after major quakes, in low, harmonic hums. This isn't rare. This isn't niche. This is the background music of the universe, and it all follows Newton. Force, mass, acceleration, all moving in perfect, predictable loops. So the next time you hear a bell, feel a bounce, watch a swing, know that you're witnessing a law, a pattern, a truth. And beneath that truth lies motion, harmonic, cyclic, infinite, predictable. This is harmonic motion, and it pulses through everything that moves. Not all motion keeps its rhythm. Sometimes it fades, sometimes it's forced, sometimes the natural swing of things gets interrupted, either by resistance or by something pushing it from the outside. This is damped and driven motion, and it's how the real world moves. Nothing swings forever. Nothing vibrates endlessly. Nothing dances untouched. There's always some friction, some drag, some nudge from beyond. And these are what shape the motion of almost everything around us. Damping is when energy is lost from a system. It's a slow drain, a subtle fade. The peaks get smaller. The movement weakens. But the system still obeys the rules, just with less energy. Picture a swing in motion. No one pushing it, just swinging. Air resistance and friction at the pivot slowly sap its energy. Each swing is shorter than the last, each arc lower. Eventually, it stops. That's damping, a force that always opposes motion, that bleeds kinetic energy into heat, and it's everywhere. In your car's suspension, in earthquake-proof buildings, in the way your voice quiets as the echo fades. Damping isn't the enemy of motion, it's its sculptor. It turns endless oscillation into something useful, something stable, something safe. Now there are types of damping. Light damping reduces motion gradually. Critical damping brings a system back to rest as fast as possible, without oscillating. Over-damping slows the return even more. Different systems need different damping levels. A car suspension needs to absorb bumps but not bounce forever. A door closer needs to shut smoothly, not slam or swing. It's not about stopping motion, it's about shaping it, controlling it, guiding it. Now imagine we keep adding energy. We don't let the system fade. We push it, again and again, regularly, repeatedly. This is driven motion. It's when an external force applies pressure in a cycle. The system is being forced, not just started, but sustained. Push a child on a swing. Each time they come back, you add a little push. If your timing is right, the swing goes higher. If your timing is off, the swing stutters or stops. That timing is everything, because when the frequency of the push matches the natural frequency of the system, something powerful happens. It's called resonance. And resonance is where driven motion becomes incredible, where small inputs build into huge outputs, where systems amplify rather than resist. The swing soars. The bridge starts to shake. The glass starts to sing. All because the input matched the system's natural beat. Resonance is not just noise, it's danger. It's design. It's opportunity. Musicians use it. Engineers respect it. Physicists map it, because when you hit the right frequency, even the tiniest force can move giants. But there's a catch. Damping still exists. Even in resonance, it limits the amplitude, prevents infinity, balances the build-up. This is why every real system has a maximum response. Why a bridge won't keep swinging forever. Why a speaker won't keep growing louder. There's always a ceiling, a damping force pulling back. But the interplay between damping and driving is what gives us real-world motion, sustainable motion, motion we can control. That's how we stabilize buildings, fine-tune instruments, design electronics, balance machines. Because every vibration from tiny to massive is shaped by this balance, between energy lost and energy added, between damping and driving. Even the human body has damped and driven systems. Your heartbeat is driven by electrical signals. Your vocal cords vibrate and are damped by the tissues around them. Your footsteps on the ground, each one a brief oscillation that fades before the next. You live inside a world of damped motion. And your actions, often are the driven forces, from flicking a light switch, to pressing a piano key, to clapping your hands, your driving motion, and the world pushes back, fades it, balances it. Even in electronics, damped and driven motion appears, oscillating circuits, capacitors, inductors, current flowing back and forth, energy moving between electric and magnetic fields. Add resistance, you get damping. Add a power source, you get driving. The system pulses, beats, transmits, and if tuned right, resonates, broadcasts, connects, all built on Newton's foundations. The key is tuning, matching natural frequencies, understanding damping ratios, knowing how much to push, when to stop, because when you get it right, the results are powerful. Energy flows, systems respond, motion becomes music. When you get it wrong, things break, structures collapse, gears rattle, bridges sway uncontrollably. So we study this, model this, respect this, because the consequences are real and the potential immense. This is damped and driven motion, where force meets resistance, where energy gets shaped, where motion finds its rhythm, and then chooses to fade or grow. It's Newton's world again. Force, mass, acceleration. But now, with feedback, with limits, with external input, with energy lost and energy gained. So the next time you feel something fade or something surge, know you're watching this principle in action. You're witnessing the rhythm of real motion, where push meets pull, where time meets energy, where movement is never alone, damped, driven, balanced, true. This is motion, as it really is. Resonance is not noise. It's alignment. It's the moment when a system, a structure, or a substance meets a force that doesn't overwhelm it, but synchronizes with it. It's when something external matches the rhythm already inside. And when that happens, everything changes. Resonance builds, quietly, repeatedly, invisibly, until it becomes impossible to ignore. Let's begin with something familiar. A child on a swing. You push once. The swing responds. Gravity pulls it back. Then again, you push at just the right time, just as it returns. Not harder, just on beat. The swing goes higher. You push again. Higher still. The motion amplifies not because you're stronger, but because you're in sync. You're not overpowering the system. You're joining it. This is the essence of resonance. A small, repeated input, matched in rhythm and magnified in response. It might seem gentle, but resonance can move mountains or destroy them. In 1940, a beautiful suspension bridge stretched over the Tacoma Narrows in Washington state. Engineers had calculated everything: strength, load, materials, but they overlooked rhythm. When wind blew through the canyon beneath the bridge, it wasn't fast or violent. It wasn't even irregular. It was consistent. A pulsing breeze that just happened to match the bridge's natural frequency. So the bridge began to move. A gentle sway. Then more. And then it twisted, thrashed, and finally tore itself apart. The bridge didn't collapse from weight, or an earthquake, or a storm. It collapsed from a whisper, from resonance. That's the danger, and the beauty. Resonance shows up in music, almost everywhere. When you pluck a guitar string, it vibrates. But the sound would be dull, without the hollow wooden body. That body resonates with the string's frequency, amplifying the sound, turning a buzz into a note into music. The same is true for a violin, a piano, a drum. These instruments are tuned not just by pitch, but by shape. The body of the instrument amplifies specific frequencies. It resonates. This is not accidental. It's physics. It's Newton's world, extended through harmonics. Even your own voice is a symphony of resonance. Your vocal cords vibrate in your throat, but the tones you hear are shaped by the resonance chambers in your chest, your mouth, your sinuses. You can change the shape of your mouth, and the pitch shifts. That's resonance. Real-time, self-control. But resonance is not limited to things we can hear. It happens inside atoms, in a microwave oven, Electromagnetic waves are emitted at a very specific frequency, about 2.5 billion times per second. That frequency just so happens to match the resonant frequency of water molecules. So when those waves hit water, the molecules absorb energy efficiently. They vibrate faster. They heat up. That's how your food warms. Not by fire but by resonance. Zoom even deeper, and you find electrons doing the same thing. Electrons orbit atoms in quantized energy levels. They don't shift gradually. They jump. But they only jump when they absorb a photon that matches the energy difference between two levels. If the frequency is too low or too high, nothing happens. But if it's just right, if it resonates, the jump occurs instantly. This is how lasers work. Light amplification by stimulated emission of radiation. A resonant frequency excites atoms in a crystal. They release photons of the same frequency, and suddenly, you get coherent light, powerful, precise and perfectly in sync. Resonance again, this time in the quantum world. And it goes bigger, much bigger. Buildings have resonance. Tall skyscrapers are not just built strong, they're tuned. Engineers calculate their natural frequencies and ensure they won't match the rhythm of wind, footsteps or seismic waves. If they do, disaster follows. In 2000, the Millennium Bridge in London opened to the public. It looked stunning. Modern, sleek, elegant. But when people walked across it, something strange happened. Their footsteps, initially random, began to synchronize. As the bridge subtly swayed, people instinctively matched the rhythm. Unintentionally, they created a feedback loop. The bridge moved more. People matched it more. Within minutes it was vibrating side to side, dramatically. Not from weight, not from structural weakness, from resonance. They closed it. Engineers returned. They added dampers, systems designed to bleed energy from motion, and when they reopened it, the rhythm was broken. The bridge was stable. So let's talk about dampers. Resonance only builds when energy is continually added and not dissipated. But damping, air resistance, friction, intentional materials limits the build-up. A swing eventually stops. A note fades. A structure steadies. Unless you keep adding energy in rhythm. That's the game. Resonance is a balance between energy added and energy lost. If damping is too strong, resonance won't build. If damping is too weak, resonance can run wild. In designing anything from microphones to motors, you must manage this balance. You even find resonance in your own body. Your chest has a natural frequency, so does your skull, your joints. When music hits just right, you feel it, not just hear it. That's resonance in your tissues. A singer can shatter a wine glass not by volume but by frequency. If the note she sings matches the resonant frequency of the glass, even soft singing can build energy until the glass explodes. It's not brute force, it's perfect timing. Electronics, they run on this principle too. Radio tuners, resonance. You spin the dial, or tap the screen, and change the resonant frequency of a circuit inside. When it matches the frequency of a broadcast signal, that signal is absorbed. The rest are ignored. That's why you can hear one station clearly while others fade. It's all resonance. Identical imaging. Same. MRI machines use nuclear magnetic resonance. They send radio waves through your body. Those waves resonate with hydrogen nuclei inside your tissue. The way they respond, the way they vibrate and release energy, gives us a map of your internal structures. All non-invasive, all through resonance. Even circuits and networks resonate. Electrical systems can experience power surges not from overload, but from resonance. A transformer hums because its internal coils vibrate at a frequency near their natural resonance. If not damped, those vibrations can amplify and damage the system. So we study resonance, we predict it, we prevent it, or harness it. There's one more layer, in philosophy, in culture, in conversation. We say things resonate with us. A speech, a quote, a moment, a song. Why? Because something external aligns with something internal. Emotionally, cognitively, psychologically, resonance isn't just physics, it's a universal pattern. When frequencies match, in sound, in systems, in souls, the response is amplified. That's why understanding resonance matters. It explains how bridges fall, how music soars, how atoms jump, how radios work, how humans connect. It's one of the quietest, most powerful forces in Newton's world. Because when energy is added in rhythm, things don't just move, they transform. This is resonance. When timing is power, when motion multiplies, when the world vibrates perfectly. Before Newton, the sky was a mystery. It inspired awe, fear, worship, but not understanding. The planets wandered. The stars rotated. The sun rose and fell. People saw patterns, but they didn't grasp the mechanics. Then Newton came along, and with him came clarity. He looked at the moon and an apple, and realized they were falling the same way. And suddenly, the heavens weren't divine chaos. They were motion, predictable, measurable, explainable. Newton's law of universal gravitation changed everything. It said that every object in the universe attracts every other object with a force. That force depends on two things: how massive the objects are, and how far apart they are. Double the mass, double the force, double the distance, the force drops to 1/4. The formula reads, in words, the force of gravity equals the gravitational constant times the product of the two masses, divided by the square of the distance between them. This equation, simple in appearance, was monumental in its implications. It didn't just explain why apples fall, it explained why planets orbit, why moons circle planets, why tides rise and fall, why comets return. It gave us a way to map the universe. And here's the astonishing part. Newton didn't just say things fall, he gave us a way to predict how they fall. Not by guessing, by calculation. Let's take the moon. It doesn't fall to Earth, not in the way a rock does, but it's always falling, every moment, toward Earth. Gravity pulls it inward, but the moon is also moving sideways fast. So as it falls, Earth curves away beneath it, and that falling, combined with its sideways motion, becomes orbit. But just like a satellite, just like a cannonball fired fast enough from a mountain to never land. This is Newton's thought experiment. A cannon atop a very tall mountain fires a ball. At first the ball arcs and hits the ground. Fire faster, and it goes farther. Fire fast enough, and it falls around the Earth. That's orbit, and it can be described with numbers, speeds, distances, forces. Newton's law made space predictable. Before Newton, astronomers like Kepler had observed that planets followed elliptical paths, but they couldn't explain why. Kepler's laws were descriptive, Newton's were foundational. Kepler said, "This is how planets move." Newton said, "This is what." He showed that the force pulling a planet toward the sun, gravity, along with the planet's momentum, created those precise elliptical orbits. Planets didn't need crystal spheres or divine chariots, they needed force. And with this understanding, humanity moved from watching the stars to predicting them. We could now calculate when eclipses would happen, when comets would return, how tides would behave. We could plan, launch, navigate. The entire age of exploration, the ability to sail by the stars, to predict the tide, was revolutionized by Newton's insights. And it wasn't just our planet. The motion of all celestial bodies, from Jupiter's moons to the rings of Saturn, became subject to the same rules. One law, one framework, across the universe. That's what made Newton's approach so radical. He erased the line between the earth and the sky. Before him, the heavens were different, pure, untouchable. But Newton showed they followed the same laws as a falling apple or a tossed stone. The universe had symmetry. This had philosophical consequences too, because if the universe followed rules, then it was knowable, deterministic, predictable, no longer ruled by gods or chaos, but by gravity. And suddenly, human beings weren't just observers, they were participants in a universe of order. This paved the way for astronomy, astrophysics, orbital mechanics, and eventually, space travel. When we sent satellites into orbit, we used Newton's equations. When we launched probes toward Mars, we used his calculations. Every planetary flyby, every space telescope, every moon landing, all of it began with Newton's math. He didn't just write equations, he gave us the tools to leave Earth. And yet, Newton's insights weren't only used to reach the stars, they were used to build our world. Bridges, skyscrapers, machines, engines, all required an understanding of force and motion. But gravity gave us the cosmos. It gave us the dance of the planets, the cycles of the moon, the light of the tides, the motion of the stars across the night sky, and all of it could be plotted, predicted, understood because of a falling apple. Now imagine you're standing on a beach. The waves pull in and out. You feel the rhythm of the tide. Most people see water, but Newton saw the moon, the pull of its gravity stretching oceans. He calculated that the gravitational force of the moon, and to a lesser extent, the sun, tugs on Earth's oceans. As the Earth rotates, different parts of the globe are pulled slightly outward, creating high and low tides. This understanding revolutionized shipping, fishing, navigation. Something as simple as a wave suddenly had a formula. He didn't just explain orbits. He explained motion. The motion of things we touch, and the motion of things we can only see. Even comets, those mysterious visitors from deep space, became subject to Newton's laws. Before, they were omens. Now, they had trajectories. We could predict their return. Halley's comet, which returns every 76 years, was predicted using Newtonian mechanics. In fact, Edmund Halley used Newton's equations to calculate its path. It was the first time in history that a celestial event was predicted in advance. And when it came back, science had won. But it didn't stop there. Newton's laws also explained precession, the slow wobble of Earth's axis. This helped refine calendars, align observatories, and understand long-term climate patterns. Even today, astronomers rely on Newtonian models to plot spacecraft paths, calculating slingshot maneuvers, launch angles, and re-entry arcs. But Newton's cosmos wasn't static. He saw the possibility of change. He even speculated on how gravity might behave in large systems. Though he couldn't know it then, his work laid the groundwork for what would later become general relativity. Einstein stood on Newton's shoulders, because Newton's universe was beautiful, but it wasn't perfect. It worked at normal speeds, normal sizes, but at extremes, near light speed, near black holes, inside atoms, it starts to break. That's where modern physics steps in. But still, for 99% of what we do, launch rockets, drive cars, build bridges, map the stars, Newton is enough. In many ways, Newton didn't just give us formulas, he gave us confidence that we could understand the universe, that motion wasn't mysterious, that the same rules applied in the lab, on the moon, or a billion miles away. So when you look up at the night sky, when you track the arc of the sun, when you feel the tug of the tide, you are watching Newton's math unfold. You are living in the universe he mapped. You are part of the cosmic machinery he helped reveal. This is Newton and the cosmos. And the sky hasn't looked the same since. Newton gave us a universe of clarity. A world where forces acted, masses responded, and everything could be predicted with precision. His laws carried us through centuries of invention, exploration, and discovery. But even the most brilliant frameworks have their boundaries, and Newton's universe, as orderly and precise as it was, eventually met its edge. Imagine you're watching a speeding bullet. Newton's laws can tell you how fast it's going, how far it'll fly, what arc it will trace, and how it will drop. But now imagine something else. Something moving, not at the speed of a bullet, but at the speed of light. Suddenly, Newton starts to slip. The numbers stop adding up. Time doesn't behave. Space seems warped. And force, it's no longer the whole story. This is where Newtonian mechanics, the classical physics that explains almost everything in our daily lives, begins to falter. Not because it was wrong, but because it wasn't complete. The first cracks appeared with light. In Newton's world, time was absolute, space was a static grid. If you were moving or standing still, it didn't matter. Time ticked at the same rate for everyone. The laws of motion were universal and symmetrical. But in the late 1800s, scientists studying light found something strange. No matter how fast you moved toward or away from a beam of light, its speed didn't change. It was always the same. This defied everything Newton had built. According to classical logic, motion should be relative. Like two cars speeding toward each other, their velocities but light refused. That was the beginning of the end for classical certainty. Enter Einstein. He proposed something revolutionary. Time and space were not absolute. They were flexible, intertwined. And the speed of light? It wasn't just fast, it was the limit. This was the birth of special relativity. Suddenly, time could dilate, stretch if you moved fast enough. Distances could contract, mass could increase, and Newton's second law, force equals mass times acceleration, no longer told the whole story. At near light speeds, acceleration behaves differently. The classical formulas break down. They were too slow for light. Then came gravity. Newton's idea of gravity was a force, an invisible pull between objects with mass. It worked brilliantly on Earth, with apples and orbits. It even held up for the moon and tides and planetary motion. But Einstein went further. In general relativity, gravity wasn't a force. It was a curvature of space-time. Imagine space not as a flat grid, but as a rubber sheet. Put a heavy ball on it. It sags. Now roll a smaller ball nearby. It spirals inward, not because it's pulled by an invisible string, but because the shape of the sheet guides its motion. That's gravity under general relativity. And that's where Newton fails, because when gravity gets intense, near massive stars, black holes, inside neutron stars, Newton's equations can't handle it. They underestimate, they oversimplify. Time slows, light bends. Newton didn't predict that, but Einstein did. There's more. Let's shrink down, past the scale of atoms, past protons, past electrons, down to quarks and gluons, the tiniest building blocks of reality. In Newton's world, motion is continuous. Cause follows effect. Objects have a place, a velocity, a predictable path. But in the quantum realm, none of that holds. Particles behave like waves. Their locations are uncertain. They don't follow trajectories. They exist in probabilities. Measure them, and they collapse into certainty. But until then, they exist as maybe, and Newton never accounted for that. Classical mechanics can't explain why electrons don't spiral into the nucleus, or why particles can teleport, tunnel through barriers they shouldn't cross. It can't describe radioactive decay, entanglement, superposition, or wave function collapse. It wasn't built for the quantum world. And so physicists had to build something new, quantum mechanics. It wasn't just a fix, it was a replacement. And it didn't just adjust Newton, it rewrote the language of motion itself. Oh, now, we live in a split universe, at normal scales. Cars, planets, people. Newton works. His equations are clean. His laws apply. But at very high speeds, you need relativity. At very small sizes, you need quantum mechanics. And when you go to extremes, when you're trying to understand the center of a black hole, or the moment of the Big Bang, neither works alone, and Newton is left behind. Physicists today are still trying to reconcile these systems, to unify gravity and quantum mechanics, to find a theory of everything, one framework that works for all scales, all speeds, all forces. That journey is ongoing, and yet Newton's legacy remains. Even in failure, he gave us the tools to begin. He gave us certainty where there was once myth, and now, with each new frontier, we learn why that certainty ends, and what lies beyond it. His limits aren't flaws, they are the edge of the map, the line between the known and the unknown. And standing at that line, we still use Newton's name, because no GPS, no satellite, no spacecraft can function without Newton's laws. No bridge, no building, no plane. Einstein and Planck and Bohr may have redefined motion, but Newton still built the road. He gave us the foundation, the intuition, the rules that still work, until they don't. So what happens at the boundary? When a particle moves too fast, or a planet collapses into a singularity, or time starts to stretch and bend, we leave Newton behind, but we do so gratefully, because he brought us to the edge. He carried us to the place where questions begin. And now, we continue, we dig deeper, we push further, we search for what Newton could not see, not because he failed, but because he succeeded so well he showed us where to look next. This is the limit of classical physics, where the numbers go strange, where the rules blur, where the universe reveals that it is stranger and grander than even Newton imagined. There are moments in history when a single mind changes the trajectory of the world. Not with a war, not with a throne, but with an idea, a principle, a few lines written on paper that crack the sky open and let clarity shine through. Isaac Newton didn't just discover laws, he revealed a structure beneath reality. Before him, motion was understood through myth. Objects fell because they were heavy. The stars moved because they were divine. The world spun because the gods willed it. But Newton gave us something radical. A reason, a rule, a repeatable truth. 3 laws. 1 law of gravity. A single framework that connected the apple and the moon, the cannonball and the comet. This wasn't just science. It was philosophy made real. It said the universe was intelligible, that we weren't trapped in superstition or randomness, that we could ask why and get an answer, that nature didn't whisper. It spoke in math. And people listened. From the moment Newton published Philosophiae Naturalis Principia Mathematica, the world changed. Scientists found in it a model they could trust. Not just in its accuracy, but in its elegance. His laws didn't scream for attention. They didn't require complexity. They were simple. An object in motion stays in motion. Force equals mass times acceleration. For reaction, an equal and opposite reaction. Gravity acts between all masses, simple sentences, infinite implications. And that simplicity was their power, because from them we could build. We could predict the motion of the planets, chart eclipses, design cathedrals, launch artillery, balance bridges, measure tides, map the Earth. Every structure you see today, every skyscraper, every aircraft, every roller coaster, every orbiting satellite, carries Newton's fingerprints. His math runs silently in the code of simulation software, in the physics of video games, in the trajectories of rockets. We trust it because it works. It always works, until you get to extremes. But for most of our world, Newton is enough. Even the engineers who send spacecraft to Saturn start with Newton. They calculate thrust, trajectories, angles, launch windows. They refine with relativity. They adjust with quantum models. But Newton lays the foundation. He tells them how to leave Earth and how to come home. And he didn't have a lab, or a research team, or satellites. He had a window, a thought, an apple. And from that he created the blueprint for classical mechanics. His legacy isn't just in physics, it's in mindset. The belief that nature can be understood. That reason matters. That observation and mathematics, not mythology, can explain the stars. He gave us a framework not just for motion, but for thinking. That's why his influence extends far beyond science. Writers invoke him. Economists borrow his metaphors, philosophers debate his implications, and engineers, centuries later, still build on his base. When we talk about Newtonian thinking, we mean more than physics. We mean the courage to simplify, the discipline to measure, the curiosity to ask, what if the same law applies here and here and here? Because he didn't stop at objects in motion. He unified the Earth and the cosmos. He connected the falling apple to the orbiting moon. No one had done that before. And in doing so, he helped define what science would become. Repeatable, predictive, elegant, grounded. He set a standard that still holds today, not perfection, but progress. He showed that the universe is not magic, it's method. And once you know the method, you can act. You can intervene. You can design and build and fly, cure. You can model hurricanes, diagnose heartbeats, time an elevator. You can lift, predict, preserve, all because a man 300 years ago wrote down what happens when you push a rock. But even that was humble. Newton never claimed he'd seen everything. He famously said, "If I have seen further, it is by standing on the shoulders of giants." He knew he was part of a chain, not the end of it. And yet, his shoulders now hold us all. The world we live in, paved roads, steel towers, global travel, orbital satellites, rests on a Newtonian skeleton, a framework of force and mass and acceleration, invisible, but essential, just like bones. You don't notice them until they're gone, and then everything falls. Even now, when we teach children physics, we start with Newton. Not because it's the end, but because it's the beginning. The gateway to understanding motion, force, energy. You master Newton before you move to Einstein, to Heisenberg, to Hawking. And for many, Newton is enough. He explains their world, their breaks, their basketball arcs, their skydives. He makes sense of the ordinary. And for most of life, the ordinary is everything. But his work also inspires wonder, because it reveals that the universe isn't just beautiful, it's logical. That the orbits of Jupiter and the pull of your body on the Earth obey the same rule. That laws don't change because you can't see them. They're always working. Even when we sleep, even when we forget, gravity doesn't pause. Inertia doesn't wait. Action always meets reaction. And behind it all, somewhere, Newton is smiling. His legacy is simplicity, not the simplicity of small ideas, but the simplicity of truth, stripped of excess, pure, like an equation written in sand, like a law carved into stone. It endures. It whispers from engines, echoes through bridges, hums through spaceflight. It guides hands, calibrates tools, times pulses, and it does all this quietly, because the greatest truths don't shout. They simply stay. This is Newton's legacy. Not just what he discovered, but how we now discover through logic, through measurement, through patience. We follow his method. Every time we test, observe, adjust, refine, and in doing so we keep his work alive, not on a pedestal, but in motion. The world still moves as he described. Mass still resists acceleration, objects still fall, force still applies, and we, still learning, still reaching, owe him more than we can measure. So we measure everything else instead. This is the final note of Newtonian mechanics, not a conclusion, but a reminder that in a universe of unimaginable complexity, a few simple laws can still explain most of it. This is Newton's world, and we're still living in it. Not all motion keeps its rhythm. Sometimes it fades, sometimes it's forced, sometimes the natural swing of things gets interrupted, either by resistance or by something pushing it from the outside. This is damped and driven motion, and it's how the real world moves. Nothing swings forever, nothing vibrates endlessly, nothing dances untouched. There's always some friction, some drag, some nudge from beyond. And these are what shape the motion of almost everything around us. Damping is when energy is lost from a system. It's a slow drain, a subtle fade. The peaks get smaller, the movement weakens, but the system still obeys the rules, just with less energy. Picture a swing in motion. No one pushing it, just swinging. Air resistance and friction at the pivot slowly sap its energy. Each swing is shorter than the last, each arc lower. Eventually, it stops. That's damping, a force that always opposes motion, that bleeds kinetic energy into heat, and it's everywhere. In your car's suspension, in earthquake-proof buildings, in the way your voice quiets as the echo fades. Damping isn't the enemy of motion, it's its sculptor. It turns endless oscillation into something useful, something stable, something safe. Now there are types of damping. Light damping reduces motion gradually. Critical damping brings a system back to rest as fast as possible, without oscillating. Overdamping slows the return even more. Different systems need different damping levels. A car suspension needs to absorb bumps but not bounce forever. A door closer needs to shut smoothly, not slam or swing. It's not about stopping motion, it's about shaping it, controlling it, guiding it. Now imagine we keep adding energy. We don't let the system fade. We push it, again and again, regularly, repeatedly. This is driven motion. It's when an external force applies pressure in a cycle. The system is being forced, not just started, but sustained. Push a child on a swing. Each time they come back, you add a little push. If your timing is right, the swing goes higher. If your timing is off, the swing stutters or stops. That timing is everything, because when the frequency of the push matches the natural frequency of the system, something powerful happens. It's called resonance. And resonance is where driven motion becomes incredible, where small inputs build into huge outputs, where systems amplify rather than resist. The swing soars. The bridge starts to shake. The glass starts to sing. All because the input matched the system's natural beat. Resonance is not just noise, it's danger. It's design. It's opportunity. Musicians use it. Engineers respect it. Physicists map it, because when you hit the right frequency, even the tiniest force can move giants. But there's a catch. Damping still exists. Even in resonance, it limits the amplitude, prevents infinity, balances the build-up. This is why every real system has a maximum response. Why a bridge won't keep swinging forever. Why a speaker won't keep growing louder. There's always a ceiling, a damping force pulling back. But the interplay between damping and driving is what gives us real-world motion, sustainable motion, motion we can control. That's how we stabilize buildings, fine-tune instruments, design electronics, balance machines, because every vibration from tiny to massive is shaped by this balance between energy lost and energy added, between damping and driving. Even the human body has damped and driven systems. Your heartbeat is driven by electrical signals. Your vocal cords vibrate and are damped by the tissues around them. Your footsteps on the ground, each one a brief oscillation that fades before the next. You live inside a world of damped motion. And your actions often are the driven forces, from flicking a light switch, to pressing a piano key, to clapping your hands. Your driving motion, and the world pushes back, fades it, balances it. Even in electronics, damped and driven motion appears. Oscillating circuits, capacitors, inductors, current flowing back and forth, energy moving between electric and magnetic fields. Add resistance, you get damping. Add a power source, you get driving. The system pulses, beats, transmits, and if tuned right, resonates, broadcasts, connects, all built on Newton's foundations. The key is tuning, matching natural frequencies, understanding damping ratios, knowing how much to push, when to stop, because when you get it right, the results are powerful. Energy flows, systems respond, motion becomes music. When you get it wrong, things break, structures collapse, gears rattle, bridges sway uncontrollably. So we study this, model this, respect this, because the consequences are real and the potential immense. This is damped and driven motion, where force meets resistance, where energy gets shaped, where motion finds its rhythm, and then chooses to fade or grow. It's Newton's world again. Force, mass, acceleration. But now, with feedback, with limits, with external input, with energy lost and energy gained. So the next time you feel something fade or something surge, know you're watching this principle in action. You're witnessing the rhythm of real motion, where push meets pull, where time meets energy, where movement is never alone, damped, driven, balanced, true. This is motion, as it really is. Motion rarely travels in a straight line. You throw a ball, it arcs, you jump, and drift sideways. A plane climbs and turns at once. A fish swims in curves. A bird loops through air. A rocket veers in a graceful bow. Newton's laws don't just apply in one direction, they apply in all directions, simultaneously, continuously. This is motion in multiple dimensions, and it's where physics becomes not just powerful but beautiful. In Newton's time, even simple motion, a rock falling, a wheel spinning was revolutionary to explain, but life doesn't move along a single line. Real-world motion is diagonal, curved, rotational, interwoven. It has depth. So to understand it fully, we break it down. We analyze forces and motion in components, directions that are easier to track. In most cases that means the x-axis, horizontal, and the y-axis, vertical. Sometimes a third, the z-axis for depth. But no matter how complex the motion looks, we simplify, we separate, we resolve, and then we reconstruct the full picture. Start with a ball thrown into the air. You give it a push, at an angle. It moves upward and forward at the same time. Gravity pulls it down. In the air, it curves. What's happening? Two motions, layered, one vertical, one horizontal. The vertical motion changes. It slows as it rises, stops at the peak, accelerates downward. The horizontal motion, it's constant, uninterrupted, assuming no air resistance. Newton's first law, the beauty lies in this. The motions are independent. Gravity affects vertical motion, but not horizontal. So we can analyze them separately, solve them with clean, one-dimensional rules, and then combine the answers. That's the core trick of multidimensional physics. Break down the problem, solve the parts, put them back together. It's like watching two movies at once, one vertical, one horizontal, and then blending the footage into a single shot. This is called vector resolution. Any force or motion that's angled can be decomposed into parts, one in the x direction, one in the y. Push a crate at a slant. It's not just moving sideways. It's also trying to move into the ground. A hill slopes downward, gravity pulls straight down, but the object slides along the slope. We split gravity into two components, one parallel to the slope, one perpendicular. Only the parallel part makes the object accelerate. The perpendicular part is balanced by the normal force, the surface pushing back. Again, Newton's third law. This method, resolving vectors, is one of the most powerful in physics. It lets us take tangled motion and untangle it, turn curves into straight lines, turn loops into accelerations. It's how we analyze orbits, trajectories, flight paths. It's how we map the future, by decoding each present direction. Now consider something even more dynamic: circular motion. A car taking a curve, a stone whirling on a string, a satellite orbiting Earth. The object is always changing direction. Even if its speed stays constant, that change in direction is acceleration. It points inward, toward the center of the circle. That's centripetal acceleration. And it demands a force, a string's tension, a car tire's friction, Earth's gravity. Motion in two dimensions isn't just about speed and angle. It's about constant negotiation between motion and force, between inertia, the desire to move straight, and guidance, the pull to curve. But let's take it further. What happens when you launch a rocket? Not vertically, not horizontally, but diagonally, through a shifting field of air pressure, gravity, and fuel mass. Now you're in full 3D motion. You're calculating pitch, yaw, roll. You're adjusting thrust in real time to correct a curved path that itself is being altered by Earth's rotation. This is Newton's world in 3 dimensions. It's not just vectors, it's systems. Every plane in the sky flies because of this math. Every drone that hovers, every football pass, every frisbee spin, every skateboard trick, all of it is 3-dimensional Newtonian motion playing out in real time. And it can all be described, predicted, modeled, if you know how to break it down. That's why we use diagrams. We draw arrows, vectors, showing direction and magnitude. We place axes X, Y, Z across the object. We measure force, acceleration, velocity, each in its own direction. We resolve gravity on an incline. We find net force in 2 or 3 directions. We turn a messy path into clear steps. And then we reconstruct the whole from the parts. That's Newton's way. Even in computer animation, this method is sacred. Characters move through digital space, not because someone draws every frame, but because physics engines simulate forces, resolve vectors, track positions. When a superhero jumps from a building, when a spaceship tilts in orbit, when water splashes in a virtual pond. It's math, underneath the pixels. Newton, every direction, every dimension, accounted for. Now think about real life. You're walking uphill while it's windy. Your body leans forward. You're adjusting to multiple forces: gravity down the slope, wind against your chest, friction from your shoes. Your muscles resolve it all. Automatically, you're a live Newtonian calculator, walking through a 3-dimensional force field, solving it with every step. Or imagine riding a bike around a curve. You lean. Why? Because if you didn't, you'd fall outward. Your inertia wants to go straight. The turn pulls you inward. You counterbalance the force with your body, creating a new vertical that stabilizes you. All of this, every curve, lean, correction, is Newton in multiple dimensions. And when you jump, you don't go straight up. You leap forward. Your legs apply force diagonally. Gravity pulls you down. You arc. You fly. And as you do, your body unconsciously splits every motion into axes. Your brain tracks it. Your muscles correct it. Your whole life, you've been solving Newton's laws in 3D. You just didn't call it that. But engineers do. They use it in robotics, where machines walk and grasp and balance. They use it in prosthetics, to mimic natural gait, in biomechanics, to model joints, in sports science, to enhance performance. Every motion broken into dimensions, tracked frame by frame, predicted, perfected. Even in space, this matters more than ever. There's no up or down in orbit. Only velocity, direction, momentum. When astronauts push against a wall, they drift in the opposite direction. Every move they make has to be planned in all 3 axes, not just position but rotation. Because in space, even a twist of the wrist can spin your whole body. Newton's third law in full 3D. We teach these principles early. projectile motion, inclined planes, two-dimensional vectors, because they're everywhere, and because once you understand motion in multiple dimensions, the world becomes clearer. You see why rain hits at an angle, why birds fly diagonally into the wind, why boats steer into current, why airplanes crisscross the sky. It's all vectors, all components, all Newton. So the next time you see something fly or fall, or soar, or curve, don't just ask where it's going. Ask how it's getting there. Break it down. See the parts, X, Y, Z, then stitch them back into a whole. That's Newton's method. That's motion, in full dimension. Some motions don't move forward, they move back and forth, then back again, like a breath, like a tide, like a heartbeat. This is the rhythm of the universe. This is oscillation. It's motion that repeats, motion that swings, motion that remembers where it's been, and returns to it, not randomly, but faithfully, predictably. And even here, even in this smooth, rhythmic back and forth, Newton's hand is steady. Let's start with something simple, a pendulum. Hang a weight from a string, pull it to the side, let go. It swings, back and forth. At first, the motion feels hypnotic, gentle, almost too simple to be worth analyzing. But underneath it is precision, timing, laws. At its peak, the pendulum stops for just a moment. Velocity is zero, but acceleration is at its maximum, directed back toward the center. As it passes the lowest point, speed is at its highest, but acceleration is now zero. Then it rises again, and the pattern reverses. It's Newton's second law in every step. Force equals mass times acceleration. The restoring force, gravity, always points toward equilibrium. And it's that constant tug back to the center that defines an oscillation. This is not just a curiosity, it's the principle behind clocks. Before digital time, pendulums marked seconds with their swing, each arc perfectly timed. Not by batteries, not by code, by physics. A swing of the pendulum, a measure of time, reliable, predictable, thanks to Newton. Now imagine a spring, stretch it, and it pulls back. Compress it, and it pushes forward. You've stored energy in it. Potential energy, and when you let go, that energy transforms into kinetic motion. The spring vibrates back and forth, again and again, until friction damping steals that energy away. This is called simple harmonic motion, and it's everywhere. The atoms in a crystal vibrate this way, guitar strings, tuning forks, car suspensions, even the vocal cords in your throat. Any system with a restoring force, one that tries to pull things back toward equilibrium, can oscillate. In fact, much of the natural world runs on oscillations. Your heart beats in a rhythm, your lungs inflate and deflate, your circadian clock ticks in a daily cycle, hormones rise and fall in waves, neurons fire in pulses. This isn't poetry, it's physiology. You are built on oscillators. And so is the planet. The tides, oscillations, the rise and fall of water, pulled by the gravitational tug of the moon and sun, two peaks, two troughs. Every day, even the earth itself oscillates. After large earthquakes, it vibrates like a struck bell, slow, deep tones that last for days. Weather, full of oscillation. The jet stream shifts. Ocean currents flip in regular cycles like El Niño and La Niña. Even climate has long-period oscillations, warming and cooling trends that span centuries, all governed by forces, all traced back somehow to Newton's rules. Now zoom out. Planets orbit the sun, not in perfect circles but ellipses. Still, the motion repeats, one revolution after another. This too is a kind of oscillation, not linear, not back and forth but periodic, rhythmic, bound by gravity. As Earth moves closer to the sun in its orbit, it speeds up. As it moves farther, it slows down. A constant give and take. Kepler described it. Newton explained it. Even stars oscillate. The sun pulses, slightly but measurably, in waves that ripple through its surface, and when a massive star collapses, it can explode in a supernova, and leave behind a neutron star that spins rapidly, its magnetic field sweeping across space like a lighthouse. These are pulsars, oscillating beams of energy, that flash across Earth with exquisite timing. So precise, in fact, that we use them to measure time across the galaxy. But oscillations aren't always stable. Push too hard, disrupt the rhythm, and chaos can follow. That's resonance, the dangerous cousin of harmonic motion. If you drive a system at its natural frequency, each push adds energy. The amplitude grows. The oscillation gets stronger, sometimes catastrophically. A bridge wobbles until it snaps. A glass vibrates until it shatters. A machine hums until it tears itself apart. That's why engineers model oscillations so carefully. They design systems to absorb vibrations, with dampers, with counterweights, with smart materials. They don't fear oscillation. They control it. They shape it. Even communication is built on oscillation. Your voice is a vibration of air. A microphone converts it into an electrical signal, an oscillating voltage. That voltage is transmitted, modulated, encoded. And somewhere else, in a speaker, in a phone, in a fiber optic cable, it's turned back into motion, back into sound. Every conversation you've ever had over a wire or a wave was made possible by managing oscillations. Now let's talk about math. Because oscillations aren't just physical, they're mathematical. They're modeled with sine waves and cosine waves, curves that describe smooth, repetitive motion. These functions appear in every branch of science, not because they're convenient, but because they describe reality, the natural rhythm of systems, the shape of energy as it oars back and forth. And then there's damping, because nothing oscillates forever. Friction, resistance, drag, they all bleed energy from a system. The swing slows, the spring settles, the sound fades. Damping turns infinite motion into a temporary experience. But sometimes, we drive oscillations. We add energy in pulses, in cycles, in rhythm. That's a driven oscillator, a child being pushed on a swing, an engine piston, a heartbeat sustained by electrical impulses. Driven oscillations are everywhere in biology, mechanics and electronics. Without them, systems would fall silent. Even your brain is full of oscillations. Neural networks fire in rhythmic patterns, alpha waves, theta waves, delta wave. Each frequency corresponds to a state, alertness, sleep, deep rest. Your thoughts, your dreams, your awareness, all oscillating patterns of electric motion. And so we come back to the idea, oscillations aren't rare, they're the norm. Nature doesn't just move, it vibrates, it pulses, it cycles, it repeats. From the ticking of a watch to the orbit of a planet, from the hum of a wire to the beat of a heart, from the swing of a pendulum to the breath of a storm, this is the language of motion. And Newton taught us how to read it, not just with numbers, but with principles, with cause and effect, with rules that echo through every oscillation, no matter how large or small. And that's the final truth. Even in repetition there is power. Even in cycles there is meaning. Oscillation is not just motion, it's memory, it's balance, it's time. And all of it, every rise and fall, every push and pull, every heartbeat and orbit, follows the same ancient laws, written not in stone, but in motion. By Newton, nothing stands forever. Not buildings, not bridges, not mountains, not stars. What rises will fall, what expands will break. What holds, eventually gives. But collapse isn't chaos. It's motion. It's structure, failing in sequence. It's forces, redistributed. It's Newton, coming full circle. Collapse is often seen as sudden, a moment of silence, then a roar. But in truth, collapse begins long before the crack, or the crumble. It starts with imbalance, with stress, with weight that exceeds support. Newton's laws never pause, even when things fall apart. Let's begin on Earth. A tower rises, brick by brick, beam by beam. It stands because its weight is evenly distributed, because internal forces cancel out, because supports push upward as gravity pulls downward. It lives in balance. But tilt it slightly. The center of mass shifts. Add more weight than it can bear. The support begins to bend. Introduce vibration, wind, footsteps, machinery, and now you're dealing with resonance. The system wobbles, the structure cracks, and eventually it yields. Not randomly, predictably. Newton's second law still applies. Force equals mass times acceleration. Only now, the force is in balance. The acceleration is downward, and the mass is everything you built. Buildings collapse when loads exceed limits. When columns buckle, they don't explode outward. They fold, one side compresses, the other stretches, and if the material can't withstand that shift, it snaps. This is called Euler buckling, and it's Newtonian through and through. A delicate structure might fall under its own weight, if its height exceeds what its base can bear. A heavy load placed too far off center causes a rotational collapse. A shift in foundation causes redistribution of stress, and failure spreads like a ripple. Engineers model collapse not just to prevent it, but to understand it, to design buildings that fail safely, to bend instead of break, to crumble in controlled ways, sparing lives, to absorb forces instead of resisting them absolutely, because sometimes absorbing is safer than withstanding. Now zoom out. Landslides, avalanches, earthquakes, all are collapses of structure, of friction, of balance. A rock face seems solid, but over time, water seeps in, freezes, expands, cracks form, weight builds, friction weakens, and then gravity wins. The whole slope shifts, mass accelerates, rock becomes fluid, the world moves. It's Newton, unleashed. Now look higher, at towers made of metal, at bridges suspended on cables. These fall too, but sometimes not from weight, but from rhythm. In 1940, the Tacoma Narrows Bridge twisted itself apart, not from a storm, but from a steady breeze that matched the bridge's natural frequency. Resonance built up. Oscillations grew, and when the material couldn't absorb the energy anymore, it collapsed. A failure not of strength, but of rhythm. Collapse teaches us humility, because it reminds us that even the most solid things are temporary. Even skyscrapers tremble, even concrete crumbles, even mountains erode. Time, weather, weight, all work in silence. And when they reach their threshold, Newton takes over. Mass, acceleration, force. Always waiting. But collapse isn't just earthly. In space, it becomes cosmic. Start with a star, born from gas and dust, pulled together by gravity. It burns hydrogen, fuses atoms, shines light for millions or billions of years. But fusion requires balance. Outward pressure from energy, inward pull from gravity. When the fuel runs out, the pressure fades, gravity wins, the star collapses. Its core contracts. Outer layers rush inward, bounce, and explode outward. A supernova. One of the most violent collapses in the universe. And what's left? If the mass is small, a white dwarf. More massive, a neutron star. Even more massive. Gravity collapses the core into a point so dense, so curved, that not even light escapes. A black hole. This is Newton's gravity at its most extreme. No longer pulling apples from trees, but stars into singularities. No longer guiding tides, but warping space itself. Even Einstein built on Newton here, using his foundation to explain collapse in the deepest sense. Because even in relativity, Newtonian instincts still apply. Mass creates force. Force causes motion. Collapse is the final result. Even galaxies collapse, merging, colliding, rebounding. Even the universe itself, perhaps, may collapse one day, a big crunch mirroring the Big Bang. Collapse is not failure, it's transition. Energy becomes heat. Structure becomes dust. Motion continues. Matter reconfigures. And sometimes collapse brings new order. A building falls, and clears space for a better one. A star dies, and forms new elements, seeds planets, gives birth to light. In destruction there is creation, in falling there is motion. In motion Newton still lives. So what causes collapse? Too much force, too little resistance, unbalanced mass, rotational stress, resonance, vibration, instability. None of these break Newton's laws. They follow them until the end. A collapse is not the absence of order, it is the fulfillment of it. And so we model it. We simulate earthquakes. We test bridges. We demolish buildings strategically. We create fail-safes. We measure tolerances. We plan for what happens when things fall, not if, when. Because in a universe ruled by motion, no structure lasts forever. Even the pyramids weather. Even the mountains fall. Even suns burn out. But in every collapse, there's knowledge, there's pattern, there's force. And where there's force, Newton speaks. So remember, collapse is not mystery. It's mechanics. It's motion reaching its endgame. It's force outlasting structure. It's mass too great, or resistance too small. But always, it is rule-based. Always, it is measurable. And always, it is Newton's world. Even in ruin. Say, it's been centuries since Newton watched the apple fall. Centuries since he penned the laws that reshaped how we understand the world. Centuries. And yet, everything still moves. Not just objects. Ideas, civilizations, galaxies, they all move. And in their motion, they obey laws written long ago by a man who saw simplicity where others saw mystery. This is Newton's universe, and it has never stopped. We began with force and mass. We followed inertia, acceleration and reaction. We drifted through gravity, soared through orbits, spiraled through oscillations and fell into collapse. But none of it, not a single arc, a single path, a single beat, ever left Newton's frame. The apple still falls. The moon still moves. And every force, every change, every shift in energy, still traces back to those few simple truths. That is his genius. That something so vast, so complex, so dynamic, the entire universe, could be described by a handful of equations. And those equations still work. We use them to build, to fly, to explore, to play, to survive. They are in your seatbelt, in your washing machine, in the engines that lift rockets, in the code that animates games, in the circuits that track your pulse, in the orbit of satellites, in the flow of water, in the silence between stars. Newton's laws aren't just historical, they're eternal. And yet, the story doesn't end with him, because Newton showed us the map, but not the edges. His laws are tools, not cages, and at their limits, they gesture toward deeper truths, to Einstein, to Heisenberg, to quantum fields and curved space. But none of them erase him. They extend him. They build upon his scaffolding. Even today, as we build telescopes to peer at the edge of the universe, as we hack particle accelerators that smash protons at near light speed, as we try to understand consciousness, entropy, artificial intelligence, we still start with Newton because he gave us more than formulas. He gave us a way to think, to observe, to test, to model, to predict, to believe that the world is not arbitrary, but lawful. And if it has laws, we can learn them. And if we can learn them, we can change everything. This is the true power of Newton's universe. Not just that it moves, but that we move within it. Not blindly, but knowingly, with purpose, with understanding, with foresight. We chart our course with physics. We light our path with force and mass and acceleration. We travel because we know how motion works, and we know how to make it work for us. This is why Newton matters, why his universe endures, because he didn't just describe how the apple falls, he revealed the framework that lets us rise. We rise on airplanes, we rise in elevators, we rise in rockets, we rise in understanding, and all of it, every upward climb, is built on the motion he first mapped. Even now, as you read this, your heart is pumping blood, your lungs are cycling air, your limbs are balancing against gravity, you are accelerating slightly every time you breathe, you are resisting inertia with every blink, you are a Newtonian machine, pulsing with motion, guided by invisible forces that you may not see, but that never stop shaping you. You live in a moving world, and because of Newton, you can measure it, control it, respect it. So when you see the rain fall, know that it obeys Newton. When you throw a stone, watch its arc. When you drive a car, feel its mass resist change. When you drop a coin, listen for the sound of gravity reclaiming it. Every motion is a signature, every change in direction, a whisper from the past. This is Newton's legacy, not a statue, not a formula, but a universe still moving, predictably, beautifully, reliably. A universe you are part of. And maybe that's the final truth. That Newton's laws don't just describe the universe, they connect us to it. They remind us we are not separate from nature. We are subject to it. And yet, through understanding, we rise above ignorance. We move with it, instead of being moved by it. So remember, when you leap, when you fall, when you turn, when you stop, when you reach, when you float, you are not just moving, you are proving. Every motion, a tiny echo of a truth discovered centuries ago. Every step, a vote of confidence in a universe that follows rules and rewards those who study them. This is Newton's universe, still spinning, still surging, still bound by the elegance of three simple laws, and still unfolding, one motion at a time. The apple fell, and we rose.